Um, am I audible to everyone? Uh, Anybody online? Can anyone respond? Okay. So now we shift our focus to one of the most pressing topics in meteorology today, extreme weather events. From high impact rainfall to tropical cyclones and polar cloud systems, extreme events are increasing in frequency and intensity, challenging our forecasting systems and resilience framework. This panel explores how cutting-edge observational techniques and ground-based radars and polar meteorology, combined with advances in numerical modeling, are helping us to understand and predict these high-impact systems with greater precision. Our speakers today represent a spectrum of expertise from radar-based storm analysis over India to boundary layer cloud dynamics over Southern Ocean and convective scale cyclone simulations and national forecasting. The session will be chaired by Professor Dr. Satishan, Director of School of Marine Sciences. Let's begin with our first speaker, Dr. Uma Kiran. Dr. Uma Kiran is a scientist at Space Physics Laboratory at VSAC. Her research primarily focused on atmospheric dynamics with special emphasis on tropical mesoscale convective systems and its associated dynamics. She investigates key dynamical phenomena such as stratosphere-troposphere exchange processes, gravity wave generation and propagation, and their broader implications for upper atmospheric circulations. Her expertise extends to the use of ground-based radar systems and satellite remote sensing techniques for observing and characterizing mesoscale convective systems. Through her contributions, she aims to improve the understanding of the vertical coupling processes in the atmosphere and enhance the detection and analysis of mesoscale weather events using advanced observation platforms. Dr. Ma will talk about tracking the rhythm of the storm, a perspective from radar observations. Over to you.
Thank you for the introduction and very good afternoon to one of the present over here. It's always a challenging task to keep everyone awake after the lunch session. So I hope I will try to do that justice to you if you don't sleep. So with that, I just start the presentation. And yes, I just tracking the rhythm of the convective storms. Basically, I meant to like rhythm in the sense like a heartbeat. So from the morning session, you have been listening to the importance of the convector systems because it brings the precipitation, the most important component, the water in our life cycle, right? And so I just get so we are I'm trying to track these storms, the rhythm of the storms, how it beats and how the characteristic changes in each and every event. So since it is a workshop and focusing on the students, I thought I'll just start with the importance of these convective systems. So as you can see over here, this is the tropical deep convective clouds that is sitting over here. And you see the temperature profile, right? Like you all know, the temperature decreases, the troposphere, and then the increase in the stratosphere, and you see the tropopause. And today morning, Rajiv sir was just mentioning, right, the clouds that is penetrating the tropopause, how much impact it will have. So when a convective cloud penetrates into the tropopause, it deposits a water vapor, and so the stratosphere troposphere exchange processes takes place. And in the other aspect, like these clouds basically form from the strong updrafts, which we talking, Tara madam was mentioning in the morning, like how these vertical winds are very important for the formation of these cloud systems. So these vertical winds basically we get from the radar. CUSAT University must be well aware of the ST radar that is situated here, right? So that is the most important radar that can give the vertical velocity in the world. No other radar can give that vertical wind. So with that vertical wind, you can characterize these kind of convective systems. And then you, of course, once the convective systems forms, you have this precipitation. And you all know the main component of our life cycle is the water. And this hydrological cycle, that is the condensation and the evaporation cycle, is basically dictated by these convective storms. So when you talk about these convection, they have a strong impact on the hydrological cycle, number one. Then once the hydrological cycle, they have, because since these deep convective systems form, they have both like temperature structure gets disturbed, and you have exchange process. And of course, they lead to the formation of the clouds, and these clouds will have the radiative impact. And once the radiation just altered, your thermal structure gets altered, your chemistry gets altered. So everything is interlinked to one to the other. And once these things gets affected, of course, your circulation gets affected. Once the circulation gets affected, your mass and the energy budget is also getting affected. So global total weather and the climate is dictated by these convective systems, because they have a large role in dictating each and other phenomena. And as the earlier speakers mentioned, they are interlinked to each other. So it's very, very difficult to characterize. And the importance when you talk about this, of course, the most important thing is rainfall. As you can see, the farmers always look for it, whether it will be a drought or a flood or any kind, what kind of the rain, because the crops basically depends upon that precipitation, and that to the monsoon precipitation. And there was most of the aircrafts avoid these kind of deep convective cloud systems, right? Because once it is, the pilot always tends to avoid this and try to go in the other direction, so that because the turbulence caused by that can be dangerous. And of course, since I'm coming from ISRO, we have most of our rocket launching systems depends upon such intense weather systems, and we do give predictions whether such kind of cyclones or convective storms or extreme weather events will happen during the rocket launch or not. So these kind of convective systems have both impact in every sphere of our life. And this is the famous structure as given by the House. Today morning also you would have seen two presentations had this specific structure, which talks about this mesoscale convective system, which has a shallow convective cell, medium convective cells, and the deep convective cells. And of course, the angle, which Mates was also talking about to characterize that annual structure. And you have a very long that stratiform precipitation. So when you talk about the mesoscale convective system, it's an ensemble of the convective storms, which is in a horizontal scale of 100 kilometers, and it should be more. And then this is the typical structure. Morning Taramam was shown from the GPM, and I'm showing it from TRMM Nesbit eta. This is the percentage of precipitation, that is the rainfall that is caused by the MCS. And you see about 70 to 80% over the entire region is caused by this MCS. And you can see this typical blue structure Rajesh sir was talking about, that marine stratocumulus clouds, right? They don't contribute much to the precipitation, but their impact is very strong in terms of the radiation cycle. And this you all know, okay? Yes, the thunderstorms have different stages. It starts from the cumulus stage, like as we are taking birth, we get matured and we die. So that is the cycle of the clouds also. Like it's slowly the cloud starts forming, that updraft will be there, and then the air parcel starts rising, and then the condensation happens, clouds will form. Because of the latent heat that is released, it aids the further development of the clouds. And that mature stage, you have both the updrafts as well as downdrafts, where you get the maximum rain. And once the clouds gets dissipated, you have the dissipating stage, where you slowly see only the downdrafts and you see the angle structure. So this is basically a structure of the system. And how do you measure? So there must be a different platforms to measure all of these systems, right? Like we have the radars and we have sensors in the balloon. Like you all must be familiar, like how these temperature, humidity, and from the satellites, whether it's an infrared or a microwave or based upon the reanalysis, several meteorological variables. So today my talk will be focusing, as I said, the tracking the rhythm of the storms only by a radar perspective. So I'll be covering the VHF, UHF radars, like similar to your ST radar, which is located at your place. And then I'll be touching upon the weather radar. If time permits, I'll talk about the satellite radar too. So the focus of the presentation goes like this. Why I've kept like this? Because of the students community, you can just see when you have a ST radar, K radar, right? It's a single point observations. You can characterize only which is coming above you. You cannot characterize the wide where somewhere it is propagating coming towards your location. No, you cannot do it. Suppose then you come to the weather radar. Weather radar, you can have a regional structure like up to 200 to 300 kilometers. That is the maximum range that you can have. So a regional characteristics of the convection can be done by the weather radar. And next comes the space-bound radar, of course, comes top, but you can cover the entire globe. But the problem is that the time resolution, right? It doesn't give every half an hour or something like that. It just, whether it's like you talked about CloudSat, Calypso, and all morning, many people were talking about, right? Those have passes only once in 16 days or something. By the time the clouds are, it pass. So you do not have continuous structure. But of course, you can get a climatology of what kind of a cloud fraction that exists over the entire globe. So you have different platforms to measure such convective systems and cloud formation. Coming to the first part, which is the ST radar I'm going to talk about, you can see, as I said, that vertical wind, the most important thing. So you probe your radar in your vertical direction and you see the system that is moving towards your radar, and you characterize whether what kind of a system that is there. So this is the vertical velocity, and generally when the radar, if you see from reanalysis, it will be order of centimeters per second. But when you see from this radar, the convective system vertical velocity is very, very high. It can go to 5 to 15, 20 meters per second. That is the movement of these updrafts that is happening inside the cloud system. That is the convective system. And so this is a very deep convective system. You can see the height is given here and it goes up to 16 kilometer. Means these kind of very deep convective system penetrates the tropopause too. And you can see the corresponding rainfall also. And one interesting event you can see here, this is also a very deep system, but that does not lead to a very heavy rain. Means what? Systems can lead to heavy rain or need not lead to heavy rain. Basically, these are caused because it's a main, and we found that it's mainly the evaporation because a drop every time need not reach the Earth's surface. It can get evaporated too, even in a dry, deep convection where you don't see any rainfall. And this is the height of the storms. You can see basically most of the storms are going like much above the 12, 13 kilometer, indicating the deep system. Then, how to characterize these terms? I'm just putting all kinds of perspectives towards you so that you can think about how to use your instrumental techniques to develop such kind of phenomena and explain the physics that is involved in these convector systems. And you can see that, you know that as we are keeping, the systems will be passing, right? So you know time t1 and you know when the system is passing time t2, right? So you know what is this overpass time over your location. So with that, you can characterize, yes, over my radar location, this is the time the system has persisted. And you see, most of the time, these deep convector system goes for 30 to 40 minutes, and most of the shallow system less than 10 minutes. And one last talk also Reshmi was mentioning, right? The shallow convection mostly comes to 10 minutes only. Very rarely it can go up to 20 minutes. So that is why you can see at 10 minutes, a shallow system persists. A deep system can go for even more than a half an hour. And then the decaying system, which you see mostly the up and the down drafts, it can also go for 10 to 20 minutes. And we have, for the first time, we characterized the shape of the system by doing some kind of autocorrelation analysis. And we found these deep systems have a very inclined structure. So when you probe with the radar, characterize the vertical velocity, you see an inclined structure, which shows that these kind of systems can live for a very long time. Because when you have an incline, your downdraft is happening somewhere so that you does cool the surface that is below here. So you get updrafts here, and so the system can persist for a very long time. And that's the reason the shape matters. That is why in a very strong sheared environment, you see such inclined structure which supports the convection. Then we try to characterize these convective systems on wet and dry spells. Like you all must be knowing active and break phases of the monsoon, which we classify over the central India region. If it is climatological rain is plus or minus 1 sigma on that day, then we classify it as active. If it is minus, we call it as rain. But this does not follow all over the Indian region. There are different because sometimes central India may get a heavy rain, but southeastern India does not get rain at all. So we have to classify based upon the regional this, that is the wet and the dry spell. And what is the interesting feature we found is that when the vertical velocity during the wet spell, we saw a single modal distribution, and dry we saw a bimodal distribution. And we found that basically the temperature and the shear, you have to keep one point, students, like when the shear is in the lower troposphere, that aids your growth of the convective system. But when it is in the middle and the upper troposphere, it doesn't aid it to mid troposphere, especially at 7-8 kilometer. That is why during monsoon system, we are seeing such kind of a system where you have strong shear and the convective system is there, it breaks it into two. So shear plays a major role in determining the structure of the convective system. Then now we are seeing with the VHF radar, right? So based upon some the FT radar, you can classify with respect to the vertical velocity. That is the only parameter through which you can characterize the convection. Now, single point is over. Next, coming to the regional thing. How in regional, as we are equipped with how many radars you can see. This is the location of all the IMT radars that is here. So we are having a variety of S-band to X-band to C-band. And recently we have in the Mumbai also a network of X-band radars is also being put. So these radars are very important to understand the regional characteristics so that we can understand the propagation and then the precipitation pattern. So today in my talk, I'll be focusing only about three aspects. One is the monsoon convection that is over the southwestern India. And then I'll talk about the hailstorms and extreme weather event that was observed by the Kolkata radar. And then I'll be talking about the cyclone which is observed by the Chennai S-band radar. Coming to the first part, this is the monsoon convection, which you have seen. Like this is our location, Tumba, like Trivandrum, where Tumba is like a rocket launching station we have. And then we have a radar that is situated here, which is a C-band polarimetric radar. And this is the orography. You can see the Western Ghats is there. And this is the typical pattern which you all must be aware. So over this region, it's very interesting because the radar is placed in such a position that you see the ocean atmosphere interaction too, like ocean to land. That ocean crossing the coast and then going to the land. And then you have, and it is the gateway of the monsoon region, of course. So you will be able to understand the orography is there. So all these plays a major role in dictating the convective storms. So this is a typical picture, like how the systems gets organized. And you can see slowly, this is at around, this is on the onset of a monsoon date, where you see a storm system that is coming over and you can characterize the vertical extent of the system. And this is called as the constant altitude plant position indicator, which you get from radar. That a constant altitude, what is the regional distribution of the reflectivity? That is what you get from this picture. And you see the reflectivity is going to 40-45 dBs. That means intense convective system is situated over this region. So based upon the reflectivity threshold, you can classify what kind of a system that is over your region. That is the first fundamental point. How do we tell? Since I told the tracking the rhythm of the storms. As I said, so we have first we saw analogy. If I try to give, like, first we see heart with like any person heart is disturbed. First we go, they tell that you take an ECG. Then if that is something is showing, then they will go to echo. Then if they tell, then they told that you do the treadmill test. So these kind of different tests for tracking the rhythm of the heart is there, right? So like this, we also can track the rhythm of the storms by this radars and then second. So with this radars, when we try to characterize, what did we do? I'm talking only about the deep and the intense convection. So which is basically greater than 35 dBs less. So in the radar, if a 35 dB is weather radar, equivalent radar reflectivity is there, and then it is of about occupying a volume in the sense X, Y, and Z. So if a 30 kilometer cube, if it occupies a volume, we call it as a deep convection, intense convection. That we call it as a storm. That is called as radar convective storm. So once you know the storms that is situated over different places, try to characterize. What you have to characterize, if I have to tell who are you will tell that suppose suppose like this, that person has some typical color. He has this hair, he has a gray hair, he has like this, right? So we also tell like convective storms, either we talk about the morphology, like how is the size of the storm, what should be the height of the storm, how much area it has extended, what should be the intensity, like that. These are different parameters. So that is what is shown here. What is the shape of the storm? Intensity of the storm. This is 35 dBs. And how intensity is spread of convective fraction. You can see both the southwestern side and the northeastern side of the radar is very much dominated by such intense convection. Then comes the shape, like we call it as an eccentricity. Eccentricity is we have a linear or a non-linear storms. So basically, what do we see? That the value, if it is less than 0.95, we basically call it as non-linear systems. And that is what you're seeing here. Very non-linear systems is dominating over this location. Then intensity. Next comes the intensity. Intensity, you see, it can go up to 55 dBs, and that is also located over the ocean, and the northeast side, that is over the land. Next comes how much height it has gone. This is the point. So this is maximum material. In the morning, I was also telling, like, throughout the radar, we have found like most of the storm top, that is the convective storm, has gone less than 8 kilometers. And that is what you see, a very blue patch over this. That is any monsoon location we take, congested clouds dominate the most during the monsoon over the Western Ghat region. And the leeward side, you have a Western Ghat, right? So the wind goes It hits the orography, and then you have the leeward side where it goes to a deep convection. And that is what you see. The leeward side has the maximum deep convection. But that percentage, when we see how much is the deep that is distributed, that is more than 8 kilometers, and we see about 30%. And this is the overshooting. Overshooting means more than 15 kilometers. It has to cross the tropopause, right? So overshooting, that we have found only 1%. So in a monsoon, when you characterize the system, we find 60% as congested and 30% as deep and 1% only overshooting. That is crossing more than 15 kilometers. But that 1% is also very important. We should keep in mind.
In case of rain outside of the northern side.
Yes, sir. This kind of, that's what I do. Monsoon convection, when you talk about over the Bay of Bengal also, percentage may vary, but most of them are congested. But the deep proportion may vary. Here we are getting 30, like 39, 35.
Northeastern region.
Northeastern region only. Northeastern regions also, we are specifically monsoon convection is not carried, but from the satellites they have observed with the GPM, mostly it is that touch less than 8 kilometers only, congested only. And so this is the vertical integral liquid, which talks about how much liquid it's like within the reflective area. And we find that in monsoon, because they are almost located at 7-8 kilometers, the liquid, vertical integral liquid is less. Based on the storm top, then you can categorize, as I said, congested, deep, and overshooting. I have already explained. And how much so we see, obviously, when there is a more overshooting convection, you will have everything will be more intense. And that is what you see here, even though their percentage is less. So you have to be very careful, even that 1% can lead to extreme rainfalls, and then it can cause maximum stratosphere-troposphere exchange. All these processes depends upon what kind of a convection that happens. And then this is the rain that you can see. That's what I said. You see, overshooting, even though the density is very less, but the rain that it causes is 20 to 30 millimeter per hour. And then you have another area that based upon, you can classify based on your area also, like whether it is less than 100 kilometers square, 100 to 1000 kilometers square, and more than 1000 kilometers square. We call it as a D scale, C scale, and B by C scale in meteorology. So, and we see that maximum this the B by C has a very long lasting duration, and D scale is about 1 hour. So D to C scale is the maximum. And we see this D scale is about 89%, means we are mostly seeing the monsoon convection over the Western Ghats on the southern western side. We see 89.5% dominated by less than 100 kilometers square. That is the area of MCS. What do we see over that region? So these radar observations are very important so that we can tell what kind of size that persists over any region. And B by C, even it's greater than 1000 kilometers, it was just 0.5%. So that's very extremely less. And then this is the typical figure which shows about the area time integral precipitation flux, meaning that how much large area, if your system is having a very larger area, it can cause a large precipitation flux. And we do see here, yes, the larger area is causing the maximum precipitation flux. Of course, that is even dominated by these D-scale storms also. Then next important component which has to be addressed is the diurnal. And we see that the propagation, as I said, diurnal propagation is a very important thing in a monsoon convection. You see starting from the southwest side, propagating, and it's going, and then there are around 12, 15, and 15 to 18, we have the maximum over the land, and then slowly gaining. So that is the peak over the land is observed between 12 to 15 LT, and you have a trimodal distribution over the ocean, which is well explained. And when you talk about the background, yes, I have seen a system, and what kind of background meteorology is supporting such systems? One comes stability, which we call about the cave, and then we could talk about the moisture, and then we talk about the moist flux convergence. And we try to understand all these parameters. And one thing, I'm not going into details, what we found is that once the system is formed and supported by the lower tropospheric humidity, and you can see very interestingly, if it occurs 80 to 90% humidity is fine. It's not going beyond 90%. The RH, if it goes beyond 90%, none of the intense storm is getting supported. It's all like RH, tropospheric, lower tropospheric humidity is up to 80 to 90% supports an intense convection over this location. That's a more high average. And we do see vertical moisture convergence is also supporting with the mid-tropospheric humidity. Cape and does not have much role in the monsoon convection. However, in a moderate Cape, we do see an intense convective storms. So it is basically the mid-tropospheric humidity along vertical moisture convergence is supporting the monsoon convective storms over this region. Coming to the next part, which is the hailstorms, which I was talking about. And this is an extreme weather event. And you can see the global map of the hail, which was taken at 2018 by Crane and Holland based upon different information. And as we all know, where are we prone? The most maximum region that we are prone for a hailstorm is northeastern region, right? You have seen maximum sometimes in the central India, but the maximum occurrence happens over the northeastern sector. In this northeastern sector, because we have the moist air mass that is coming from the ocean and the dry air mass, which we call as Kal Baisakhi, the nor'westers. These nor'westers comes and these convergence happen, and they are very, it's kind of a frontal systems because one is dry and another one is moist. So when such kind of systems, it leads to a very deep system, and that deep system results in the formation of hailstorms, and you see the squall lines. And these are the regions, and this is with the curtain. This is a typical structure. You can see a small system that is forming, leading to a squall line, and then a hail forms. So such kind of systems is predominantly seen during this nor'westers, that is over the northeastern region. You see a typical, you see beautiful structure. It gets organized from a small storm. It gets organized, form a linear line of storms, and then slowly dissipate. And such kind of beautiful propagation can be seen with the radars. And this is just a typical plot. Like we try to, suppose now I have seen a hail. So what should I do? I should understand when these hail forms, what kind of convective storm results in hail. Every convective storm, every day we are not seeing hail over that region, right? Only on a typical cases we see. Why do we see? That is the main study we did over this location. And this hailstorms, we got about 32 hail days. 32 is still that is a number. Over a region of about 10 years, whenever the island is reported, we have taken the radar and tried to analyze what is the convective storm that is causing hail. And we see mostly non-linear convective storms with a maximum, and the time that occurs also, it's about 9 to 13 UTC. This is the time when we see maximum hailfall over this region. And they have a maximum of 55 dBz of reflectivity. And then the height of max that is about 4 kilometers. And one important criteria which we remodified was the Foote-Crosse criteria. It is basically talks about when a hail will happen. Like over that region, you have about 3 kilometers. What did we do is that when the Z max is about 45 dBz, you have to have the reflectivity from the radar. So if it is more than 45 dBz and it is crossing the freezing level, we mark it as 3.5 or 4. So that kind of 55 dBz should be more than the freezing level, and it should persist for a little higher altitude of about 1.5 kilometers. So if that is the case, those systems have definitely led to hail over the ground. And that is this Foote-Crosse criteria, which shows that most of the time it is between 3.5 and 4. And then the question comes, yes, every storm you said it cannot lead to hail. And then why dust does not lead to hail? And we have found this is the hail and this is a non-hail. And we find the most interesting aspect is that the vertical integral liquid and the vertical integral of hail mass did not support that storm to reach the hail. And you see here, vertical integral of hail maximum going to 2 to 4 in a hailstorm, and the vertical integral of liquid is between 50 and 100. But you see a non-hail case, even though a thunderstorm is formed, which is very deep, but its integral of liquid and its integral of hail did not have those values to cause the hail on the ground. Then the background condition, we found that this is the cave, and there's a vertical velocity at 851.5 kilometers, and this is a specific humidity. And we found that just before 2 hours, even from the reanalysis, it can be found out that just before 2 hours, how these values vary. And then this is the 0. 0 is the time when the hail fell down, and this is minus if we are going ahead in time and behind in time. And we found, yes, at this point, 2 hours before, we see a slight increase and then a fall in all the parameters. And very important parameter we call, that's what I said, lower tropospheric wind shear, which is between 0 and 6 kilometers. We call it as the bulk wind shear or the bulk wind stress. And that for the hail is much more higher than for a non-hail case. So hope you all are not sleeping. Not sleeping? Yes. Then let's go into the last part. We have the cyclonic storms. I talked about extreme weather, right? We talked about the extreme rainfall during the monsoon, how it happens, what kind of a convective storm can cause. And then we came to the hail, what kind of a convective storms can lead to the formation of hail. And then coming to the cyclone. Yes, in the cyclone also we have small convective system. Mesoscale convective system gets embodied within the cyclonic storm. What should be that variation? So this is one particular typical case. You can see the formation and you can see the track of the cyclone, and then you can do this mostly in the East Coast, where we see the Bay of Bengal, we have the maximum number of cyclones, even though we see these days over the Arabian Sea also discussions are keep on going, but still we have the maximum number over the Bay of Bengal. And this is a typical picture. These animations are like you can get out of sleep by seeing some videos. So that is the purpose. Nothing great in this. Just to see the evolution of the cyclone, and you can see the eye. Can you identify? Yes. Here is the eye sitting in different location. Here is the eye. Here is the eye. How beautifully you see a system. It's eye propagating eye wall, and then inner rain bands and outer rain bands. You can see very beautifully pictorially represented with respect to the radar. So what is the important aspect? Why I should? Yes, I have seen eye wall, inner rain band, outer rain band. Yes, I have seen. What should I do with that? I should understand what kind of convection caused that within that system. So we designed a methodology to identify the eye, and from that we design eye wall, inner rain band, outer rain band, and outer region, and trying to characterize the convection in each of these regions. And that is what it's shown here. It's the eye wall here, it's the inner rain band, and outer band reflectivity. Reflectivity talks about the strength of the convection. And you see, mostly in the eye wall, you see the refractivity goes up to 18 kilometer, and you see a very inclined structure, which is a typical characteristics. Today morning also, you would have seen a presentation, a convective system, how an inclined structure of these reflectivity with the radar is seen. Because such kind of an inclined system lasts for a very long time and can penetrate vertically too. And in the inner rain band, you see up to 14 to 16 kilometer outer and outer. So such kind of characterization can be done where the intensity of these convection can be formed within the different regions of the cyclone. Next, it is very interesting to see how the cyclone it starts from the depression, right? It forms depression, deep depression, cyclone, severe cyclone, very severe cyclone, and then comes back to SCS and then comes back to CSD. This complete evolution, how it happens. And this radar can track such systems, the weather radar. And you've seen, this is the depression. We are seeing the intensity is very less, intensity is strong, compared to that of cyclonic storm. And you see a kind of a beautiful bimodal distribution. One is the shallow and then coming to a deep. But in the CS, you see a very beautiful structure going up to 16 kilometer, and the SCS also. And that's like in the dissipating stage, you can see a different typical pattern during the formation stage of severe cyclonic storm and during the dissipation stage. Very interestingly, we found that we are still investigating during the dissipating stage, because your intensity remains much more stronger compared to the formation stage, because there you get the maximum convection, maximum rainfall as it crosses the land. It makes the landfall. It makes the landfall, you see a very deep convection and then a rain. And that dissipation is also clearly seen that when you see during the formation state and the dissipation state, you get much more intense convection compared to the formation stage. And this is the typical characteristics where we found that, yes, the morphology of convection within the cyclone. And still here also, as I said, the cyclonic storm we see mostly on the north. If you see, this is the center, you see north. The northeast side of the radar has the maximum compared to this southwest part of the radar. And then now, if time is there, I just have 2 more slides, or else I'll wind up. Can I continue? Yes. So just till now, I've talked about the single pointing radar. Yes, VHF radar with the vertical velocity. And then I characterized with respect to the weather radar, with the reflectivity, how you can characterize the convective storms, and morphology can be brought up. Coming to the satellite, if I see from the top, what do I see? Because I cannot see what do you see from the ground. The vision is entirely different, right? So let us see how do we. So that opportunity we got once when the Aura series of satellites were launched. CloudSat, Calypso, Yamalis, Parasol, what not. It gives the entire structure of these clouds and what kind of chemical exchange processes happens. All these informations were beautifully brought out by the series of satellites. And this is one such study where we have seen, morning I talked about just now before, like wet and the dry spells, and Rashmi was also talking about the wet and the dry spell rainfall distribution, right? And so today, then we also tried to see, because the clouds radar was there. Rajesh sir was mentioning, right, a radar and the LiDAR, so you can characterize the different types of clouds. So we tried to understand during the All India active and the break phase how the cloud distribution is there. And this is the active, you can see the black and then the red color. Very interestingly, you see the low level clouds is mostly dominating over the active spell, but during the break spell, there's a cloud top height. The height is maximum during the break. Means height is maximum in the lower atmosphere during the active and height during the break phase, and that is supported even by the cloud-based height also. But when we see the geometrical, we see this geometrical depth is very extremely less. Means these are high altitude clouds. These high altitude clouds are a typical phenomenon which we call it as a cirrus. That is the optically thick cirrus, thin cirrus, angle, all these come under this classification. You have a deep convector system that is penetrating, and then they get diverse, and that can go for a very larger area because of your background wind. And especially during the monsoon, you have the tropical easterly jet, right? So when these clouds is formed, and when these angles are formed, and this tropical easterly jet is also located at that region, so they also flow, and this can go very. And even from the Indian monsoon region, we have seen the propagation up to North African region too. So that is the kind of these cirrus threads can be seen during the monsoon. And that we have tried to classify like based upon its optical techniques. Thickness only. If thickness is more, it's angry. If thickness is less, it's thin. And much more less, we call it as subvisible. So that is the characteristic, that is a subvisible, thin, thick, and dense cirrus. And we find the thin cirrus is dominating. And during the break phase, we have the subvisible and thin mode. And thick, you see, it's ulta. Thick, we see active convection, means active phase of the monsoon when your convection is very strong and you see a very thick cirrus. And these thick cirrus have a very long lifetime, and then they slowly become thin cirrus. And that's why during the break phase, you see the reminiscence of these thick clouds. That is what is being seen here. And how to characterize the cloud inside it? Either with the liquid water content and the ice water content, right? And here you see the liquid water content and the ice water content. And you see liquid water content is more in the active phase and the ice water content is more in the break phase. That supports, yes, the cirrus remnants is much more in the break phase. Yes, I've characterized the Indian. This is my last slide. I have characterized India, yes, fine. Then how do my Indian monsoon is different from the rest of the monsoons? Vangitar gave the definitions of these different monsoons. You know other monsoon regions, right? We have an Australian monsoon, we have North American monsoon, we have North African monsoon. Here I'm talking only about the Northern Hemispheric monsoons, where we see East Asian, Western North Pacific, Indian summer monsoon, North African monsoon, and the North American monsoon. And we see a very beautiful cloud fraction. And we see during the monsoon, the cloud fraction is very high over the Indian summer monsoon. And then we try to classify the low level, mid level, and the high level clouds. And here sits the Indian region. You see the low is where comparatively less, middle is dominating, and high level, of course, very much dominating, which is similar to the Western North Pacific. So the Western North Pacific and the Indian summer monsoon have more or less the same kind of the cloud structure when we see from the top. And this is the reflectivity factor, which we see typical, which shows the structure. Like here, you see this is called as the bright. So the bright, it's about 4 to 5 kilometer. Morning also there was a rainfall. Convection, stratiform, the radar sees the bright band, which is that because of the what do you say, dielectric constant of the water droplets, you see as a melting level in the bright band. Because dielectric constant is high and the melting process happens at that region because of your temperature is around 0 at 4 to 5 kilometers. So when the rain is coming from the top, you see a kind of a bright patch. And that typical structure you see here, it's a very steep over the Indian summer monsoon compared to the other monsoons. So, and when we see the ice water content, we see this is the Indian monsoon. So when we take about comparison of these kind of the monsoon systems over the entire globe, we find Indian summer monsoon, of course, is the strongest with the Western North Pacific. So yes, I did. Like you have seen, yes, you have seen from the single point radar, you've seen from the weather radar, you've seen from the top, but still questions always remain, where am I standing? Why? Yes, because it's basically the complex multi-scale interactions. With the cloud systems also, you have a lot of interactions that is taking place, which is really very, very difficult to understand understand the observations as well as with the modeling. And then you have limitations, of course, because we don't have a suite of observation to study one particular phenomena, right? We have different located and different time scales they are seen, different spatial scales they are seen. So it is very difficult to coordinate such kind of instruments and get a comprehensive picture. And then, of course, the natural variability, because you have within that itself, when the system changes, it's very difficult to predict and to understand, yes, how do I do? No, it's very difficult. So even though we understand many building blocks of cloud and precipitation physics, integrating these into a coherent picture remains always a scientific challenge. I hope maybe one of you sitting over here will be able to address that in future, and addressing the open questions involving advanced observations, because we should have, I feel I always have a dream like we should have a system in a mobile kind of a band facility where have you seen US and all like that? There are several movies on the thunderstorm tracking and all those things. I've forgotten. So they take the radar, they take all kind of instruments within that, and they keep on go behind the tornadoes. So like that, I also feel that when the monsoon starts, we have to keep a kind of a mobile based facility with all the instruments sitting and track the system, keep on traveling with that. With that, I end my talk. Thank you one and all for listening. If you have not slept, question should come. Justice will be done. What could be the probable difference that I would see in the hail and non-hail experience? Yeah, basically what did we see is that hail, when we looked with the thunderstorms cases, we didn't find the reflectivity. Reflectivity thunderstorm intense means it can go to 35 to 45, right? In the hailstorm convection cases only, we saw the reflectivity going more than 55, 60, 65. That was the limit. But within the thunderstorm that did not cause hail, maximum was 45 to 50. So that is the first. And then, as I said, then we found that the storm extending, because anything can be a thunderstorm, but the top that it is going to a higher altitude was about 16 kilometers, 16 we could observe. But for the non-hail cases, we observed maximum 13, 14, like that. And coming to the vertical integral liquid was about 50 to 60 kilogram per meter square, because that only can withstand, because the microphysical processes happens. But for the other, especially we saw less than 10, 20, even though it was a thunderstorm. So these were the three important specific reasons which we found the difference between the hail and the non-hail.
Questions from online? No. What is your take on different environmental background settings of different type of systems? Because systems have to be prepared in the background.
Yes. That's what I talked about. I think you must maybe, like, for example, like when we talk about this monsoon convection, the background basically that's true. But very interestingly, what did we find? That's what I'm telling. Very interestingly, when we see the northern Bay of Bengal with the Kolkata radar observations, and when we see from the southwest to monsoon, this thing, both are entirely different. That's about the monsoon system. But both the monsoon systems were occurring only in a moderate cape and only supported by the mid-tropospheric humidity. And very interestingly, we found that even with these, when the divergence, when the vertical moisture flux convergence were negative, also sometimes we do see a system. And this similar case was even observed in the Australian also. Australian monsoon also found that the moderate cape and with the mid-tropospheric humidity. Exactly, mid-tropospheric humidity exists. But when we came to hail, yes, of course, the things are different because the shear plays a major role, the Balkan shear. That is the background environment. Otherwise, other than that, Yes, no, that is in the northeastern side. So that basically happens in the pre-monsoon. And the pre-monsoon, we do find that because of the strong shear needed, the bulk wind stress, what we talk about, that only has caused the maximum to tear and raise to hail. When did we either see the cyclone? Cyclone, of course, is a large scale, which is determined. Properties. No, I don't think because whatever we have seen from the radar is for the last 10 years, like from 2000, yeah, that didn't have much kind of an impact because the monsoon sets as it's like the place are like, but the convection properties remains the same. We have tried year to year also, we have seen day-to-day variability also seen, and overall on a climatological perspective, we have not seen other than the extreme hail events, extreme rain events occurring suddenly and vanishing. But the morphology remains the same. It has not impacted much, maybe because our observation also with the radar tends to a very short time. Exactly, yes. Yeah, that's it. We started from 2007 up 2017, the observations from radar at Southwest Coast monsoon. Now it's 2025. 8 years we have seen the morphology remains the same with the convective storm. That's what I just thought, like these kind of parameters, rather than putting it from the top or this in the model, like this should be the structure of the system. This is the lifespan of that system, and this is the height of the system. If we are able to input these, because I'm not a modeler, basically I come from experiment. If we are able to put these things into that model, I think that will lead to a better understanding of these kind of extreme weather events or what kind of system will go for the future. Other than that, simply putting like, yes, the winds and the other things, it doesn't make any sense.
Different stages of propagation of monsoon broadband. What about the change in radar reflectivity or morphology in different stages of
Yes.
monsoon broadband? Can you elaborate?
So different stages, like in the monsoon propagation, what we have seen is that basically you are talking about one single region, or you are talking about the northward propagation over the Indian region.
Yeah,
North, we should have a set of continuous observation from the ending, starting from the south, and you should have it up to this. But my focus is basically was with the southwestern this thing only. There only we have seen only the propagation coming from the land and then hitting the coast and then going to the southwest, the northeast side, and then the northeast side is getting intensified, and then that cycle gets repeated with the early morning to the afternoon and that kind of thing. But if we plan a coordinated set of instruments in the west coast of the radars, as I said, we have like yes, you see, we have like Kochi, of course. Kochi, we have Trivandrum, Kochi. The problem is that since it's a sea-band, we could not see Kochi. We had maximum I've restricted to 120 kilometers. Attenuation is more in sea-band. But Kochi has yes-band. That's really amazing thing. So I always, so this, and then Panaji, and then Mumbai, and then Mumbai also has 4 X-band radar network now. So if this full radar is utilized continuously from that, and with this, we will be able to understand much better. There should be a coordinate observation starting from the south, how the northward propagation happens, how this intra-seasonal cycle is changing, what is the physics, microphysics that is going inside the system that can be well answered within that. And but this Kochi also has very like ST and weather radar together also. The dynamics can be addressed in a month because in the radar we just can only indirectly derive or something. But with the ST radar winds and then the monsoon cloud radar, we will be able to understand this a little bit more.
Features of cloud in the Arabian Sea region and Western Ghats Hilly region.
Yes, sir. That actually I showed you.
Yeah.
This I cannot tell it as a cloud because it's a convective storm only we are tracking. Intense convective storm. I cannot talk it as a cloud. So, but what do we
During monsoon.
during monsoon? So this is specifically during monsoon. So what do we see basically as you see here? It's like most of this, as I said, congested storms only is happening over the oceans, and very overshooting type happens only on the leeward side of that. Yes, and but that percentage, as I said, is extremely very less. It's only 1% because that aids. It has to cross, and that intensity has to maintain so that once it hits the guards, and then the surrounding environment condition pushes it to it, so it can go to overshooting. But on an old we see like about deep and the congestus, and the congestus is dominating in the monsoon convection.
In the leeward side, do you think any resemblance to CB cloud?
Yes, sir. Maybe we have not mapped it. That's why I said this is a convective storm mostly when it, because when we see a deep overshooting convective storm crossing like 15, 16 kilometers, of course it should be a cumulonimbus which is a very, very vertical extent. It should be. Thank you.
Thank you, Dr. Uma, for the very informative and detailed presentation on storms. Now, as a token of appreciation, we would like to present a moment and invite Dr. Satishan to hand over. Now we will move to our next panelist, Dr. Srinath A.V. Okay. There's a slight change in the schedule. Now we'll have Dr. Jayakumar, a scientist from NCMRWF, for the discussion. Dr. Jayakumar, scientist D, NCMRWF, is leading the atmospheric modeling group of NCMRWF. He has played a key role in adapting the recent NCMRWF unified modeling system for the UK Met Office. He led the development of NCMRWF version of seamless prediction system enabling convection per meter scale to urban resolution model. Dr. Jayakumar is the principal investigator from India for the Weather and Climate Science for Service Partnership India UK sub-K modeling project under the Newton Barber Fund. He developed the DMK model for high resolution PM 2.5 and visibility forecast for Delhi and NCR region. Some of his major contributions include the development of visibility parameterization in the high-resolution Delhi model for fog forecasting, a revised lightning forecast formulation, and the development of the urban canopy scheme using Delhi's morphology data. Dr. Jayakumar was awarded the Certificate of Merit by MOAS in 2018. He will talk on impact of cloud microphysics on the track prediction of tropical cyclone Vayu in a convective scale model. What's it?
Thank you, Steve, for giving me the present. And first of all, thank you, Dr. Abhilash and all the conveners for inviting me. So, changing the schedule, sorry, I need to go to Delhi, and so that's why some changes in the schedules. But I was so happy with coming back to CUSAT and meeting my sir itself. I think, and it's wonderful that we have recently started MOU with the Cochin University and National Center for Medium Range Weather Forecasts, and a lot of good students are coming. And this work itself, your one of student is also in there, Rose Raphael. And obviously, I need to acknowledge our collaborators, interface, and my colleagues. And this work is mainly yeah, fine. Yeah, so this is one of the paper came in the QGRMS last week, and we need to give us some background about. I think most of the people know that our operational centers looks into very heavy precipitation, severe weather from a convective scale model. So I need to give some background about the convective scale model. And this paper is about a very difficult prediction system that is a recurved disease. So that's happened in 2019. So, and we'll slightly, since it is a panel discussion, I thought of having a discussion about how good your model in predicting this type of recurve cyclone system, look at the large scale atmospheric conditions. Then we'll look at the role of cloud microphysics process in this tropical systems, cloud distributions, and come to the dynamics. That is how effective your latent heating on this. So I request all to go through this paper, and more of the details are in this paper. Starting from the convection parameter model, as we know that the convection parameter model currently it is operationalized and giving a real-time products from the 0 and 2 UTC up to 3-day forecast, and it is covered the all India up to a 4-kilometer domain. And here I use some observation. Sorry for using the observations. And so from 2022, we upgraded into new science configurations. And the new science configurations, main changes are happened in the it's in the double moment calcium microphysics and the bimodal cloud schemes. So major changes are previously we use a single moment that's called a Wilson-Ballard microphysics and the PC to cloud scheme. So these are the two changes from to the new science upgradations. So whenever we go to upgradation, we look at the main how much it improve in the precipitations and the lightning flashes. So if you can see the skill score between the RI22, RI3, that is a new science, and we see that many of the thresholds diffraction skill score is increases. So that's why when we're looking into the before going to any application, we check the statistics and how good the model is able to predict this type of extreme precipitations. Coming to microphysics, I think most of the earlier our delegates has mentioned about how important your microphysics. Since so why and here it is the CASIM, we call it Abri CASIM, is a cloud aerosol interactive microphysics. And in here, the previously in single moment, your most of the cloud number is diagnosed in your mass. But here, you will have a beautiful size distribution will be there. And in here in the CASIM, it considers the main hydrometeor species covering cloud droplet, waving cloud ice, snow and gravel. So these are the main 5 hydrometeors. And this CASIM, currently in the 4 kilometer, we are using from the climatological aerosol. And in for the chemistry, we are also giving operational products to the PM 2.5 and visibility. So there we couple with that very inline chemistry. And inline chemistry is interactive chemistry that is called UKCA. And you see, if you come into the model time steps, because in the casting, where the green is the casting component in the model time steps. So, especially in the model, if you see, you have two components. One is the mostly physics one component and physics two. And these are basically, in the model dynamic core, it is a semi-Lagrangian. It's considered in the advection schemes. So this advection scheme connection from the physics 1 to physics 2, and this within the iteration loop, it gives the cloud liquid water and cloud fractions, which is giving an input to your activation schemes. Slightly technical, but I think most of the things you will be interested once you're working on the model. And this background, I think I don't need to be back because already my previous years has beautifully presented, because in a deep convective system, most of the warm rain process, I think Rashmi has mentioned how important droplet activations when you have a CCN, when your condensation is there. But if you look at a deep convective system and you can see a different isotherm, you can see 0 degree and minus 14 degree. The separations of heterogeneous ice nucleation and the homogeneous ice nucleation levels. So in the model, I know most of the observation people will be surprised. Still in the heterogeneous, in the ice production mechanism, it is doesn't look at depending on the source. Still, we use the Cooper where the parameterization is depending only on the temperature criteria. And once in the deep connected system, we come to the similar to accretion process in the warm rain. There is a process called riming process. You already know that the riming process. In the riming process, you will get a large bigger length of its cognitive balance. And the one of the recently in this gas, other than the primary ice process, in the modeling it started is called a secondary ice process. So most of the secondary ice process, it's called, there are a lot of secondary ice processes there, but in our modeling currently we have included only the Rhine spindling process. So Rhine spindling process happen specifically if you look at happen in the -8 degree to -3 degree between 6 to 8 kilometer, and Rhine spindling happen in the presence of a very heavy Rhine grapple. And in the association of cloud liquid water with particular mass, then the Rhine will be spindled. So means the heavy grapple will be spindled into a very small type of ice crystals. So why I'm saying that this type of calcium schemes, there are many limitations are there, but we can include one of the secondary ice process. So these additional secondary forces can be included, then your prediction will be much improved. And the most unfortunate thing is that the secondary ice process, you don't have a much observation is also not there to look at the secondary ice process. And the second one is the bimodal cloud schemes, and in currently maybe different from what our bimodal cloud scheme is calculating the cloud fractions and cloud liquid water, as I mentioned in the first slide. And here, compared to the previous one, that is called the PC2 schemes, there is an improvement in the cloud fraction and the RX variation because of the multimodal distribution in the temperature and the humidity. Why I'm saying that most of the unimodal way, it considers the turbulence in the surface. That means here the PDF draws its variance from the not only the turbulent property in the surface, it also considers the entrainment zone. Because most of the entrainment zone, your dry air will come, and both that property or that both variants will be considered in the bimodal cloud schemes. And here, as I mentioned, the CASIM is a cloud microphysics schemes, and this cloud microphysics scheme, depending on the cloud scheme, because the cloud scheme will determine how much amount of water vapor will go to the ice and the liquid phases. And I'm not going into more detail in the right panel because the difference in the bimodal cloud scheme and the PC2 is mainly how much the advection time is interactive in the modifying the thermodynamic profile. Because of the modification of the thermodynamic profile, your latent heat will be modified. And these all are important once you're going into a very, very extreme events. Okay? So I discussed about that. First is the change in the cloud microphysics scheme. That is from single moment to double moment we change. The other changes in the cloud scheme, that is from the PC2 to bimodal scheme. So why we look in the Vayu cyclone? Because all the operational models have given a very wrong landfall over Gujarat in that time. And because of if you see look at the top panel, where the observations, RI3, which is upgraded science, IMDA is the reanalysis. I think many of the students are using nowadays IMDA reanalysis. And RI2 was the operational version of the old configuration where it has given a wrong landfall to Gujarat. So when wrong landfall information given, then what happened? The most of the disaster communities and people are evacuated, and so that's the importance of the forecast. So then what I am showing in a very experimental design is that, so the RA3, which I mentioned in the first two slides, where we are upgrading the science, and the experiment one, in the experiment one, instead of the CASIM, we have replaced only with the Wilson and Ballard, that is single moment. And experiment two, that corresponds to RA2, that is the orange line. And if you're looking at the experiment, even in the orange line, gives a similar characteristics of operational models, which is experiment 3. So it is same as RI3, but is replacing with the my model and the PC2. And finally, one more experiment we've done. So it is showing how much important of SIP process in the model. So in the CASIM microphysics, and the bimodal is there, except secondary ice process have been turned off. And so if you know that most of the people, if you saw any single deterministic run, they may not be robust. So what we did is not only a deterministic model, we even run with the ensemble criteria. So here I am showing the RI3 and experiment 2. So if you see that it's the ensemble run also, the RI3 show a very clear of recurvature. But in the operational model, which is corresponding to experiment 2, it is showing a landfall. And so, as a background, I think even Dr. Abhyas has also mentioned about how important your background conditions. So, if you're looking at the background condition of any recurvature system, we have to go into some old paper by Jayanti has shown that. And this I have taken this from the old paper. So, what they have shown in a recurvature system for a different month, especially the current Vayu cyclone was in the June month. And in the Arabian Sea, the best favorable latitudinal position is around 21.3. And even that paper, it shows that before the recurvature system, there is a strengthening of your upper air westerly wind is there. So you can see that upper air westerly winds are strengthened when it is very close to your recurvature system. And if you're looking at the value cyclone also, there is a, if you look at the at top, there is a strong westerly trough is there. And there is an anticyclone on the mid-Arabian Sea. And there is also a anticyclone over the Indian Sea. So all these synoptic wind systems are showing a very multiple interactions with your wind field. So in any movement of a tropical cyclone, there is a very main factors, as you know that first is the steering flow. So steering flow that is governed by its environmental conditions. And obviously, you know how much it is important the initial condition or the location system. The third one, which is very important, that is the beta effect changes. It is beta effect is mainly due to asymmetric convections that is coming from your convection process or the latent heating. And so here in the top panel, in the reanalysis already you people know that it's a reanalysis, and the RI3 is our new science where it has a recurvature shown, and another is experiment 2, it is wrongly shown the landfall. So if you want looking at the environmental conditions, so we have used a TC vortex method. So in the TC vortex method, it is removing the non-divergent and irrotational wind component from your total wind. So it giving your environmental wind conditions. So if you look, consider the RI3 and experiment 2, you can find that there is a, so because in the both experiment, RI3 and your experiment 2, your boundary condition is similar. So your large scale environmental structure is similar because it's a single nested model. There is no double nesting model. So, but still we find that in the experiment 2, there is a slightly more steering is happening in the near to the Gujarat where the most landfall is happening. So why that is happening? That's why we went to the microphysics. And if you compare the precipitation, the top panel is from the your IMD gridded report, and the RI3 is there, your recurvature happened, and the experiment 2 your landfall happened. So you compare your precipitations and the liquid water part from the Moody's, and you can find that most of the your cloud structures and the outer layer, where Madam also mentioned in the previous time, how the TC's cloud structures can be seen in the even in the Moody's picture also. But in the experiment 2, most of the liquid part is over the land regions. So the steering flow is, as I mentioned, that there is a slight difference. That difference is mostly by the changes in your cloud microphysics or that we can discuss. And for that, to look at the cloud microscopic and the precipitations over the cyclone track. So for that, we have used another method is called TC following approach. So if you look, if you take any fixed domain, some of the time, because some experiments, it go to the landfall, some it is going to the recurvature. So you cannot fix any domain. So better if you can using some type of a TC following approach. So it is TC following approach is like a some type of a moving 2x2 grid box domain for the both observer and model track. So throughout your forecasting period or through your convective system, so this all are based on your Hemming tracker on observation and the model. So if you look at this, actually in the, no, this is outside. So this is outside because you can have a Hemming tracker or something in the observation. You have a tracker. You have yeah. So the most of the this precipitation and the cloud top height and the cloud base height we have for the same forecast period, but it is based on your tracker. Yeah. So the main difference, because as I mentioned, there are a lot of experiments to looking at the what is the nature of or the which is making that changes in the landfall. So if you remember the RI3 and the experiment 2, that's why I'm repeating that two experiments. So if you're looking at the RI3 and the experiment 2, if you see that from 48-hour forecast, there is a clear-cut increase in the MSLP. That means it is going to the landfall where your MSLP is increases. But there are experiments where the experiment 3, I don't know, you remember experiment 3? The experiment 3, still Casim is there, but bimodal scheme was not there. So in that type of experiment, what you find is a very higher amount of grapple. So when you have a very high amount of grapple, what will happen? It will fall down. It's melting like a melting to the lower level. So it reduces your ice cloud coverage in the above altitude of 12 kilometers. Or so some type of a, so that can be seen in the this color. I don't know what is this color. You can see that. But in all other experiment, your cloud top height is a much higher. Okay, so and MSLP, I mentioned about the intensity because even in the some of the reviewers also asked how much intensity is influenced in. So that you can find in the most of the nature from your MSLP also. And this is the vertical distribution of the hydrometeors from liquid water, ice water, rainwater, and grapple, and the cloud fractions. I am only showing the RI3 and experiment 2. And as you see that, the most of the differences happening in the first is the grapple distributions. So in the RI3, and your ice process is very nicely captured in the RI3 because of the two things, because your bimodal cloud scheme is well enough to supply your supercooled water above your freezing level, and your casing scheme is able to use that supercooled water into a rhyming and other process, which is making a ice water content. So, so if you can see the ice water content and mostly having a grapple here, and the grapple is formed where it is in the zone where secondary ice process is there. So that's why in your model, you have to think that how much your SAP also is coming important in the tropical mesocell convections. And as I mentioned, unfortunately, we don't have that type of observations here. And so, so in the message from this slide is that when you use, and if you're taking a vertical cross sections of rainfall, cloud, and ice water, and specifically the recurvature system, you are getting a very vertical profiling. But in the other experience, especially experiment 2, you can find in the land regions where the your hydrometer distribution was there. And I'm not going into detail, but this slide is very much important for the product models. Why? Because most of this difference can be taken in by looking at the fall velocity. So how we can calculate in the model in the fall velocity, or we call it sedimentation rate. So it is calculating based on the snowfall rate of the model level divided by your total ice and snow water content. So if it's a mixing ratio into the density gives your water content. So if you're looking at the sedimentation rate or the fall velocity, the RI3 is your old new physics and experiment 2. So major difference is coming. There is a very nicely wider distribution of fall velocity, a wider distribution of fall velocity depending on your PSD. And the second one is your, as I mentioned, you're having a secondary process is also there. So I don't know if you can notice that with this 5.7 to 7.5 kilometer, there is an increase in the fall velocity. But if you're looking at other experiments, it is mostly monotonically decreasing. So in the casing, you find this type of SIP process where the most of the ice sprinters are there. So because this ice sprinters will be carried by your tropical system storms are very abrupt, and even it will take in a much higher level where you will find some type of a increase in the fall velocity up to then because of the above that you find a similar wider distributions. And in the lower level, I think from the morning onwards, this latent heating things already you are seeing that. So, so if you're looking at the RI3, you're having a very nicely in the middle atmosphere heating is there. So this dash line is the latent heating only from the microphysics, and the solid line is the delta T or the latent heating only from the cloud scheme and the boundary layer mixing. So if you're looking at the RI3 scheme with wider distribution sedimentation, and you having a very nicely heating, latent heating on the middle atmosphere, And below your methane layer, you are having a cooling. That cooling can be there here also. But in compensating that, you can see a warming from the cloud scheme here. So the net pattern is like as you see in the Robert House paper, like the same thing is happening in the RF configuration. If you're looking at the other experiment, I'm not going to the other experiment detail, but if you look at the experiment 2, where the landfall, wrongly showing the landfall over the Gujarat, where your cooling is only in the 5 kilometer, very close to the mythic layer. So the distribution of heating is not properly coming in a older microphysics scheme, which is not coupled properly to your cloud scheme. Okay, so these are very important when you're going into an operation environment, because you expected a very nice prediction of your deep convective system and all, but whether your microphysics or your aerosol scheme is relevant for, or is prevalent for that. So, lot of experiment, lot of research is required, especially for improvement in the tropical system. Now, up to here, we have discussed about cloud microphysics and latent heat. Now, we need to connect how your microphysics is how latent heating from the microphysics is connected to dynamics. And it is mainly connecting, as you know, that one of the very good tool is called the potential vorticity conservation. It's not a simple potential vorticity. Potential vorticity conservation is mainly by a source of diabatic heat and the friction. So in a model, your source of diabatic heat is from a different terms, not only for the microphysics, radiations, boundary layer, everything will be considered in that. So you can pick, so which term is impacted by your diabatic term. So the top panel, as I mentioned, top panel is just a temperature increment. It corresponds to latent heating. But even in the lower panel, if you in the lower panel, this is the potential vorticity term by the microphysics. And the top bottom panel is from the PVT from the cloud pressure adjustment tape. So I don't know, you remember that I don't know, because this was really a challenging for us. You see, we thought that because of the microphysics, the recurvature but if you're looking at the experiment 1, where we have even replaced with the CUSAT microphysics, our system is recurvature. So that made a very comprehensive from this PVT analysis. So if you look at the PVT analysis, specifically from the microphysics and the cloud pressure adjustment, because from the my model to your PC2 scheme, there's a difference in the cloud pressure rebalancing. So if you see in the experiment where the recurvature happening, where your PVT from cloud pressure is showing over the ocean, but in the other two regions, your cloud pressure rebalancing PVT theme is only showing in the land. So that means, as I mentioned previously, even though in the old experiment, your clearing flow from the environment is similar, the changes comes from the proper coupling of your cloud scheme and the microphysics. And this I'm not showing because the skill is improved skill, we are not interested. And this also is a future scope. Future scope nucleus parameters depending on simply depending on your temperature. So we have to go, and it is independent of aerosol. So some observational people like they made a new IND parameterization because this region where the Gujarat and this region where lot of dust and the fills for mass fraction is making a lot of in climatological ice, a lot of ice nuclei concentrations are there. So that's why the current our operational model, we are not coupled to the chemistry. So even we can test it that by coupling with the chemistry, it will be improved. So summary of my talk is the DC value in developed in a climatological favorable latitude, but it show a false alarm of landfall in the old physics, while CASIM and the bimolar cloud scheme, which is properly coupled, impacted to follow observed track. And the new physics exhibit a role of PSG formulations and SM ice productions, which sustain a wide distribution of ice fall speed and especially accretion process from the Rhine process, the release of latent heat and the middle atmosphere, and the cloud pressure rebalancing time in the models modulate the lower atmosphere heat profile. So when you're having a heat profile modulate in the lower to higher level, obviously this will be changed your vorticity time also. And because of vertical distribution of heating from lower to middle atmosphere, it changed the. So basically, we are going with the first one. We are going to the beta effect, which is making a realistic TC motion in the model. Yeah, thank you.
Do you expect that the similar physics only will be there for any other cycle, the cycle, which is really covering this thing, so that you can tell that well before this will take this path? Is it possible?
So first of all, the curvature cyclone sample is very less, as you know that in the total, very rare and all. And these cases, as you know that when you evacuate people, lot of loss for the Indian government. And your question is very valid. That's why I mentioned you, because not only for the recovery system, special focus modelize, not only modelize, even the observation people have to give to the second phase process where most of the mesoscale convective system, not only for the global system, back, I talk, about. You have to, because now our mission milestone is started. You have to think about some type of a that thinking about campaigning about not look, even I don't know, maybe from the radar also, you can think about how we can separate out the secondary ISIS process from your primary ICE process. So that or maybe students and all they can come up with. So it's not specific for the our current recurvature. The characteristics is mostly similar for the other cyclone systems. Not only DC, even for mesoscale current system, like any score lines or anything system will be here. But very understudied over Indian regions. Yeah. Yeah. Yeah.
Even after crossing the land, that it has to be. I don't know whether you see the tunnel cyclone. That was even persisting. The eye of the cyclone, because generally you don't see. The eye of the cyclone, even it was there after 3 to 4 hours after crossing land, and even over the land in the southern this thing, we saw the eye of the cyclone.
Oh, okay.
And
Yeah.
then only dissipated. Very whether this side or whether the secondary eyes.
Yeah, yeah. I think
Because generally we don't see such cyclones. I was seen for 3 to 4 hours even after making landfall. I was seen at the land.
okay. So so I request students also because lot of research is required, because I mentioned about only Rhine splintering, only one of the process in the SIP. There are droplet shattering, and there are a lot of other secondary ice process also. Because most of the primary ice process and the warm rain process are the observation people are very nicely catching it. But now because maybe the other mid latitude or their region may not be that much important secondary ice process. So that's why I think in the tropics, modelists have to consider this thing. Yeah.
Thank you, sir. That was very informative. Now I invite Dr. Satishan to present a small token of our appreciation to Dr. Thank you, sir. The last speaker of this panel is Dr. Srina Devi. She is a postdoctoral research fellow at Monash University, Australia. She is dedicated to advancing the understanding of convective cloud systems over Southern Ocean. As a part of the Securing Antarctica's Environmental Future project, his research focuses on the dynamics of open and closed mesoscale convective clouds. Srinath is exploring their interactions with atmospheric dynamics and thermodynamics, as well as the impact of climate change on Antarctic environmental conditions. He'll be talking on the impact of synoptic meteorology on observed surface heat fluxes and boundary layer clouds over the Southern Ocean. Srinath.
Hi, can you hear me? Am I audible?
Yes, yes.
Okay, then I will. Hi, good afternoon all, and thank you for giving this wonderful opportunity to talk in this workshop. And today I'll be discussing about how the large-scale synoptic meteorology influence air-sea interaction and boundary layer clouds process over Southern Ocean region. Southern Ocean plays an important role in regulating global mean temperature. It accounts for almost 75% of the global oceanic heat uptake. Studies have found that the variability of sea surface temperature over Southern Ocean can influence the global circulation pattern and also long-term climate trends. The CMIP 5 and CMIP 6 models are showing continuous warm bias over Southern Ocean region. This warm bias of SST in this model is mainly due to the errors in the representation of boundary layer clouds and cloud phase and their fraction over this domain. Previous studies noted that the synoptic scale weather pattern influenced the boundary layer structure and also clouds over Southern Ocean region. Based on the K-mean clustering technique, Larry et al. Identified 7 major weather regimes over Southern Ocean domain. Most of these weather regimes are connected with the passage of frontal system over Southern Ocean. They have identified a unique cluster named C2 near the coast of Antarctica, which is mainly associated with the characteristics of katabatic wind flow from the continent of Antarctic region. When we are talking about the boundary layer clouds over Southern Ocean region, mesoscale cellular convection is a particular type of cells or clouds frequent over this domain. Based on the cellularity, these clouds are categorized into open and closed mesoscale cellular pattern. In open cell, clouds are present at the edges and the centers are cloud-free. In closed mesoscale cellular convection, clouds are present at the center and the edges of these convective cells are cloud-free. The efficiency of precipitation is higher in open cell in comparison with closed mesoscale cellular convection. So in this study, we are trying to understand how the large-scale synoptic meteorology, boundary layer clouds, and air-sea interaction connected over Southern Ocean region. Based on that, we are formulating 3 research questions. In first, we are trying to understand how the weather regimes and mesoscale cellular convection influence the variability of sensible and latent heat flux over Southern Ocean. Next, we are trying to understand how the thermodynamics of atmosphere is regulating the interaction between synoptic scale regime and boundary layer clouds over Southern Ocean. Finally, we are trying to evaluate the performance of ERA5 over ERA5 fluxes over Southern Ocean region based on observation during different weather regimes and MCC conditions. For that, we are first using sea surface fluxes from a station or mooring-based observation, which is known as Southern Ocean Flux Station, located at 47 degrees south and 142 degree east. And this mooring provides long-term observation from 2010 to 2023 period in 1 minute resolution. In certain period, the data sets are not available because of the maintenance issues of the mooring. We noted that around 38% of the data is missing from this during this time period. For understanding the cloud pattern, that is open and closed MCC, we are using Himawari satellite imagery to distinguish the both open and closed mesoscale cellular convection. Here, the classification of synoptic type or large-scale meteorology is done by using K-mean clustering techniques on ERA5 data. For K-mean clustering technique, we have using 4 variables at 3 different levels at Southern Ocean Flux Station location, along with 3 surface variables which include pressure, air temperature, and relative humidity. The analysis was carried from 2010 to 2023 period. To understand the thermodynamics of atmosphere, we are using 2 terms or 2 indices which are known as estimated inversion strength and marine cold air outbreak index. Estimated inversion strength provide an idea about the strength of capping inversion that is existing in the atmosphere. Marine cold air outbreak index is calculated by taking the difference of potential temperature at surface level and potential temperature at 850 hectopascal level. And this parameter will give an idea about the potential for convection at the lower level. Based on the K-mean clustering technique, we have identified 5 major synoptic regime or weather regime over Southern Ocean region. Here, the first panel represents the spatial distribution of rainfall, mean sea level pressure, and wind at 975 hectopascal for each regime. The middle panel represents the thermodynamic profile of each weather regime. Bottom panel represents the 72-hour back trajectories of air parcel at 1 kilometer range from high split trajectory. When we are considering the first weather regime, which is termed as high pressure regime, you can see a high pressure is sitting over southern part of Australia and which is extending towards Southern Ocean Flux Station. The star mark represents the location of mooring. And this particular regime is associated with very less amount of precipitation over the domain and weak northwesterly wind. When we are analyzing or when we are considering the vertical profile of temperature and dew point temperature, you can see a strong inversion is existing over atmosphere associated with this particular weather regime. When we are moving on to the second weather regime, which is known as Tasmanian blocking high, a high pressure is sitting over Tasman Sea, and this particular weather regime is associated with a moderate lower level wind and a moderate amount of rainfall. When we are considering the temperature and dew point temperature profile, a strong inversion can be seen from 950 hectopascal itself. The next weather regime is named as zonal, where the wind is mainly coming from westerly direction. This zonal pattern provides moderate amount of rainfall over Southern Ocean Flux Station region. When analyzing this SCUT log P diagram, you can see a moderate inversion is associated with this particular regime. The fourth regime is named as frontal, and this particular cluster is associated with intense rainfall over the buoy location. and a low pressure is sitting south of the mooring location. And it is associated with strong air mass from continental region. And the vertical profile of or the SCUT log P diagram represent an unstable or deep layer of instability existing when frontal system is passing over this particular region. The final cluster is named as cold air adduction. This particular weather regime is associated with passage of southwesterly wind from higher latitudes of Southern Ocean. When analyzing this SCUT log P diagram, we identified that this particular cluster is associated with moderate level of inversion, temperature inversion in the atmosphere, and the air mass is mainly coming from high latitudes of Southern Ocean. The seasonal characteristics of different weather regimes at Southern Ocean flux station is given here. It is evident that cold air adduction shows cold air adduction and Tasman blocking high shows strong seasonality. Cold air adduction is peaking during Australian winter season. Tasmanian blocking high is peaking during summer season. Other three regimes like frontal, zonal, and high pressure regime is not showing any particular kind of seasonality. You can also identify that zonal is one of the most frequently occurring weather regime over Southern Ocean flux station. This particular figure represents the box plot analysis of observed and ERA 5 produced sensible and latent heat flux for different weather regimes and MCC condition. We identified that most intense release of sensible and latent heat flux is occurring during cold air adduction. And it is around the sensible heat flux during cold air adduction is around 3.5 times higher than the overall mean of sensible heat flux. And the latent heat flux is around 2 times higher than the overall mean of latent heat flux during cold air adduction regime is passing over Southern Ocean flux station. When we are considering the Tasmanian blocking high and frontal system, we identified that the sensible heat flux is transferring from atmosphere to the ocean. This is mainly related with these two systems are carrying warm continental air from southern part of Australia to the mooring location. So sensible heat flux is transferring from atmosphere to the ocean associated with these two weather regimes. We also find that during zonal regime, the sensible heat flux exchange between ocean and atmosphere is mostly in equilibrium state. The comparison of ERA 5 fluxes with observation is given here. We identified that ERA 5 is performing significantly better in reproducing observed sensible and latent heat flux over Southern Ocean flux station. It is having a correlation of around 0.94 sensible heat flux and 0.92 for latent heat flux. However, the performance of ERA 5 fluxes varies with different weather regimes. In zonal clusters, the sensible heat flux bias in ERA 5 is minimal, and frontal clusters shows maximum bias of sensible heat flux. When moving to the latent heat flux bias, Tasmanian blocking high is representing or showing minimal bias of latent heat flux in ERA 5, and cold air adduction showing most significant bias in latent heat flux. The relationship between sensible and latent heat flux with M index is given here. The color scale represent the values of estimated inversion strength during that period. We identified that during high pressure regime or Tasmanian blocking high, there is no particular relationship between M index with surface heat flux, and the atmosphere is associated with very strong inversion as we seen in the SCUT log P diagram. In other three regimes like zonal, frontal, or cold air adduction, we notice that both sensible and latent heat flux increase rapidly with M index under weak inversion strength. We already see that cold air adsorption is produces significant air-sea interaction over Southern Ocean flux station region. And this significant air-sea interaction is associated with higher values of M index and lower values of estimated inversion strength. This particular figure represents the frequency of open and closed MCC clouds in association with different synoptic types. We noted that cold air reduction producing maximum occurrence of open MCC over Southern Ocean. Closed MCCs are more prevailing in association with high pressure ridging. The QT log P diagram of open and closed mesoscale cellular convection is given here. In open MCC, we identified a weak inversion from 800 hectopascal and a strong lower level wind. In closed MCC, what we observed is a strong inversion layer is existing from 900 hectopascal level, because these particular cloud types are mostly frequent during high pressure ridging. And the wind velocity is also very less during closed mesoscale cellular convection. When we are analyzing the sensible and latent heat flux during open and closed mesoscale cellular convection, we find that there is not that much difference in the release of sensible and latent heat flux during open and closed MCC. However, there is a significant difference in the precipitation rate. Open MCC is producing around 1.6 millimeter per day over that particular region, and closed MCCs are less efficient in producing precipitation. It is only producing 0.7 millimeter per day in average. So we have calculated the entrainment rate in open and closed MCC and noted that open MCCs are associated with a very weak entrainment, around 1.6 centimeter per second. Closed MCCs are associated with very strong entrainment or dry air entrainment, having a value of 4.3 centimeter per second. So this dry air entrainment can likely reduces the precipitation efficiency of closed mesoscale cellular convection. Further, we already see that a very strong inversion layer during this closed MCC that will inhibit the vertical growth of cloud, thereby reducing the precipitation efficiency. The relationship between M index and surface fluxes for open and closed mesoscale cellular convection is given here. In open MCC, we identified that this M index is mainly ranging between -5 to 0. And in closed MCC, it lies between, or it is distributed mainly between -15 to -5. Further, in both open and closed MCC, sensible and latent heat flux increases with M index. However, in open MCC, the rate of increase of sensible or latent heat flux is higher with M index compared to closed MCC. So the key findings from our research is cold air adsorption showing strongest air-sea coupling over Southern Ocean region. The two high pressure regime named by high pressure regime and Tasmanian blocking high are associated with very strong inversion layer, and there is a weak relationship between fluxes with M index. Next, ERA 5 exhibit a strong agreement with observed sensible and latent heat flux over Southern Ocean, characterized by very low bias and high correlation. The final point is relatively small difference in surface fluxes between open and closed MCC suggests that the synoptic scale meteorology plays a dominant role in controlling the precipitation efficiency of these two shallow convective clouds. Thank you.
Thank you, Dr. Srinath, for your valuable insights into the southern hemisphere climate. So, can we have few questions? Anyone? I think many of the people are yet to understand what this southern hemisphere holds for them.
Yeah.
So many of them are mostly studying in the northern hemisphere, so not much. They're yet to understand the climate and everything in southern hemisphere. So, so thank you, Srinath. Any questions online? Okay. So thank you, Srinath, for your talk, and I hand over the mic to Steffi.
So we are at the end stage of this panel discussion. So now let's have a photo session to mark this day. I request everyone to come forward.
Partha sir,
Hi.
good evening.
Yeah, good evening.
Yeah, actually, we are breaking for this session. We'll
Okay,
start in
yeah.
after 10 minutes.
Yeah,
So we'll
no
start
problem.
with your presentation first.
Fine, fine. So I'm logged in.
Is that okay?
Yeah, no problem, no
Because
problem. So I'm logged in.
yeah,
So whenever you start with the
either you keep login and we
yeah,
will be back.
I remain.
Yeah,
No issue. I remain logged in. Okay.
we will be back in 10 minutes. Okay.
No issue. Okay.
Yeah. Thank you.
Let's go for tea now and come back after 10 minutes. Yeah, be here sharper for it.
Take the office.
That time.
Hello. We now come to a final panel of the day, observation and modeling of convective storms, which brings together emerging and established voices working on the observation, analysis, and modeling of convective storms. The insights shared here will not only inform model development, but also help strengthen impact-based forecasting and early warning systems. I now invite Professor Mukhopadhyaya. He is a visiting faculty member at the Indian Institute of Science, Education and Research, Berhampur. He has a deep expertise in the development of high-resolution numerical models and physical parameterization, particularly cloud convection and cloud microphysics. His research focuses on extreme precipitation forecasting, high-resolution ensemble prediction systems, and the prediction of intra-seasonal oscillations in the monsoon. He retired as scientist from the IITM, where he led the indigenous development of a 6.5 kilometer resolution Indian global model over the tropics. He also headed the Niti Aayog Departmental Action Plan of MOES on developing a high-resolution global ensemble weather forecast model. He was the elected fellow of Indian Academy of Science in 2023 and the member of WMO Weather Research Program Working Group on Tropical Meteorology Research. He is also the recipient of certificate made by MOES in 2015. Professor Mukhopadhyay is going to discuss about the challenges in representing convection in NWP models. Welcome, sir.
Yeah, okay, thank you. Thank you for kind introduction. So, should I share my slides? Or? Yeah. Let me know if I'm audible, everyone. So, could you see my slides? Is my slides visible?
Yes, sir. We can see it.
Okay, just 1 minute. And can you also tell whether it is moving? Slides are moving?
Yes, sir.
Oh, great. Okay, thank you. So let me start my timer. Okay. Okay, so thanks a lot for kind introduction, and thank you, Dr. Vilas and all the organizers of International Commission on Tropical Meteorology, as well as International Association of Meteorology and Atmospheric Science, also CUSAT and everyone involved in this one-day brainstorm. I was actually traveling from Calcutta today, so I missed all your other panel and talks. So I may not be able to do justice. I may repeat something, or I may not be able to connect my talk with other talks. So please excuse me. And so the topic has been given is that challenges in representing convection in NWP model. But to do justice with the topic of the brainstorming session, that organization of convection and extreme. Okay, so I will emphasize on this. Okay, organization of convection, because we are still struggling. The whole globe is struggling in capturing these organized convection. Okay, now what it is, what do we understand about these, etc., and what the models do about this. So those all things I will discuss. You can see there is a lot people who worked with me, contributed. So it is not just my work alone. There are people from outside India as well. They are my collaborators. And okay, so now my next slides. So yeah, so this is my outline. Okay, so I will give you an introduction on organization. And then I will try to emphasize that what does the observation suggest about organization of convection. Then I will touch upon where does the model stand in resolving the convective organization, and what are the approaches, strategies that we can take up, okay, possible for cloud and convection organizations in NWP models. Now, this is a paper. I would suggest all students here to, 1 minute, let me take the pointer in. Yeah. So this is a paper by Mitch Moncrief, our friend and collaborator, back in 2012. I will recommend all students, again, to read this paper again and again. It's an excellent paper published in Bulletin of Society. And the name of the paper was, the title was Multi-Scale Convective Organization. I underlined it. Why? Because the emphasis was on multi-scale and then convective organization. And then there was a virtual field campaign. Every time we feel that for any field campaign, we have to spend huge money and huge manpower, everything. So Duane Wallis and Mitch Moncrief, they conducted a virtual global field campaign. Okay, and it's called a Year of Tropical Convection. Please read this paper. Now this figure is from that paper. Okay, and these, of course, these arrows I have put. It was not there in the paper. What is shown here is very interesting. It is a photograph of a cumulonimbus cloud that we know from our basic geography background, and a satellite image of a mesoscale convective system, which is here. Okay, and the bubbly regions in the stratiform cloud bed are overshooting cumulonimbus clouds, and you can check, you can appreciate it easily, showing that a multi-scale character of convective organization. Okay, and bottom, what you see here is the global distribution of total precipitable water. Okay, and derived from SSMI, MSRE. Okay, and microwave imagery from Cooperative Institute for Meteorological Satellite Studies. And that total precipitable water, you can very easily see that's very high over the tropical warm ocean, is very low over the tropical region, but there is a connection. You see here what we normally believe. So somebody can say it is atmospheric river, somebody can say it's tropical interaction. So now what you see in these three figures, okay, if you show it to anyone, so you can see, you can tell, okay, and before that, let me tell you, this arrow I have put to just to emphasize that this is the area of entrainment, this area of downdraft, this area of strong updraft, and these are the areas where you have entrainment, detrainment. That's why the cloud looks like a cauliflower. It doesn't look like a cylinder. Okay. So what does this three figure together give us? It gives us that, see, this is a large scale, right? This is a large scale moisture distribution. Inside that is embedded is this mesoscale convective system, and is the ingredients. What are the masala? What are the components? These are this, okay? And these are the processes, okay? Now, if I want my model or anything to capture this whole thing, okay, I have to capture each element of this, okay? I cannot just simulate this cloud and tell my model I'm great, or I cannot just look at this large scale thing without, taking care of this cumulonimbus cloud and tell, look, my precipitable water looks very nice, okay? It will not work. So unless otherwise we take into account this multi-scale nature and elements, we are not going to do justice with this convective organism. So number one. Number two, from the same paper, okay? This is a famous figure by this one. Yeah, you see, this is a famous figure by Bob House, and this is kind of similar, okay, similar to what the figure previous slides. It also shows anvil. Below anvil, there is a strong, downdraft. You see, this is cold downdraft. That's why it is the color of the arrow is blue. Okay, and there are shallow cells, then there are medium cells, then there are deep cells, deep convective overshooting. So this itself shows a multi-scale nature. This shows the kinetic energy. Okay, this is the pressure gradient, the work done by pressure gradient. Okay, And so this is the whole thing, and which is actually which one letter worked on, that this is the area of strong latent heating, which was not included by Bob House. So added much later. So this is the area of heating. So actually, to exactly explain the whole system, you see the heat and the circulation is coupled. So this is convectively coupled as well. Now, this is the whole, see, this is the picture. What is this picture? This is the TRMM picture of, of precipitation features greater than 100 kilometer, okay, which is something around MCS. And you see here, remember the total precipitable water, this thing, and you can see it is very well matching, right? So where you have total precipitable water maxima, you have this MCS maxima, you have all these, embedded MCS happening, and so that's how we get the total, complete picture of the global precipitation distribution, global MCS distribution, and the complete general circulation. So this is the, please keep this in mind. And this has come from that virtual, virtual experiment, YOTC. Okay. Now, see, in the same paper, this is given. Okay. So what are the, source? No? What are the data that you, me, anybody? These are all free. Okay. So what are the data? Virtual experiments. So nobody has gone and actually took any, right? So what are the data? What are the data source that has gone in explaining all these things? Is all this, see, Calypso, series, MLS, AIRS, SNWF analysis, MODIS, CloudSat, AMSR. So, and what are the parameters? See, it is written here. So any student now, you can go and download and follow this paper for your region, for your state, okay, for India, for ocean, for any region, you can go deeper. Okay, now these are the time series of this data are longer. This is I'm talking 2012. Now we are 2025. So right, another 13 years of data has gone into this. You have got a much more larger data set. It is fantastic. Okay, so please look into this. Okay, now what is the hypothesis that is coming out from all these experiments? Purely observations. Okay, look at this diagram. Okay, this is beautiful diagram. Again, by from the this thing from the same paper. You see carefully. It shows here. You see it is diurnal cycle, right? Here you see seasonal cycle, right? And you see inside they are all connected. So diurnal cycle. Okay, 1 to 10 kilometer cumulus cumulonimbus connected to mesoscale convective system, 100 kilometer connected to synoptic wave, 1,000 kilometer connected to MGO, 10,000 kilometer and contributing seasons. Okay, so this is the multi-scale. Okay, and you see there is an upscale effect, there is a downscale effect. So it means that the meso or MGO, which is a very large scale, low frequency, wave number 1, affecting cumulonimbus organization. On the other hand, the cumulonimbus, which is of a kilometer scale, is affecting the large scale. Okay, so and you see in the right hand side, they have also given a prescription. What should be the the typical delta X? It is 100 meter, 1 kilometer, 10 kilometer, and so on. Now here, one very important thing they noted, and that is valid till today. Okay, there are 3 points they have listed. Mesoscale convective organization bridges the scale gap. Very, very important. Mesoscale convective organization bridges the scale gap. So if I don't have a parameterization for mesoscale convective system, so I miss the scale gap. Okay, so I will never be able to simulate the variability realistically. What they suggested is that SCM or CRM resolves cumulus. We all know two-dimensional cloud system resolving model like superparameterized global model. They resolve MCS, but high resolution global numerical prediction model crudely represents MCS, and till date we don't have any parameterization that represents the MCS. So he mentioned in 2012. It is valid till today. Okay, this is an open problem. Now, coming to model, I think you all know this figure. It was the famous Princeton experiment. Any computer, one Neumann standing here, Potop standing here, and Jules Charny standing here. Okay, and so this was the numerical modeling experiment. Why I'm showing is that you see this was the experiment they did. So this CFVN means C is Charny, Potop, and von Neumann model, CFV. Okay, so they were very simple. They were just trying 24-hour prediction. A 500 hectopascal geopotential height. Now anybody can do that. Okay? So the geopotential height is thick lines, and absolute vorticity is thin line. What is plotted here? Okay, and they were just trying to predict 6 January, taking 5th January initial condition, predicting 6 January. Okay, now this is initial analysis. This is final analysis. So from here they want to go here. Okay, and you can see there is a kind of system here, low pressure or whatever it is. It has moved here. Okay, and this is nothing but the difference. Okay, forecast change. Okay, so and this is it is a forecast side. So basically, what is this here is this minus this. Okay, so you see, actually, model in today's standard will tell it's did not do very good job because the system has moved here, where actually it was over here. There is a slight shift, okay, to the left. But still, in 1949, it was a big deal, okay. So this is what forecast change is the forecast side. So this was the time 1949. This is the figure I show everywhere, okay. It is actually from one of our paper. We were just plotting, very simple. We were also trying 24 hours, okay. But what we were trying to do is the upper level divergence and low level convergence during monsoon onset. What we expect, I mean, this is analysis. Okay, there's a final analysis. So what final analysis is showing? It is showing that from 29th May towards 31st May, divergence is moving northward. It's quite natural. The low level convergence also is moving northward, right? This is quite natural because monsoon is also and it is targeting northward. But when we see just 24-hour forecast, we plotted from the same NCEP GFS in 2006. You see, it is not showing any, neither in divergence nor in convergence. You see 1949, and you see in 2006. So this is the bottleneck. So it is a very large scale signature, but the model is not capturing that either. Okay. Now this is from a regional model. So and the GFS is a global model, but this is a regional model, WR. This is from another old paper, 15 years back. You see, this observed northward propagations. Okay, the monsoon doesn't come continuously; it comes in pulses. Here you see rainfall, one pulse, then there is a lull, then there is a pulse. Right? It comes like piecemeal way. But you see, we tried 3 convection scale, both Bestmiller, Ken-Fries, and Grell, whatever. And you see, the model doesn't show that pulse. It keeps on running. It keeps on running. So neither it is so. So this is the issue. So this is one of the issues. Now this is a paper very recent, 2020. Okay, L. Bock and Lauer and many people, they have trying to quantify the progress across CIMI-5 model. Okay, and look at this. This is CIMI-6. Okay, rainfall bias, CIMI-5, and CIMI-3. Okay, look at the mean bias. So CIMI-6 was 0.2, this was 0.27, it was 0.153. So bias has actually, increased in CIMI-5 and to some extent, reduced to CIMI-6. But overall picture, you see, the signal is that the ocean is running more, land is running less. Dry bias persists over land, and wet bias persists over ocean. So it means my model is running more over ocean, less over land. But we live over land. So, and heavy rain or extremes happening over land is more important than over ocean. So this model, I mean, all these models, they're not still doing the expected thing. CFS is not an exception either. You see, CFS also reigns over ocean, both the low resolution and high resolution, both, and less over land. Okay, so but then in the same paper, okay, the same 2012 Moncrief et al. Paper. See, they said that, see, if I ask you which one is the observation and which one is the model, actually it is very difficult. So they suggest that if you go to a very high resolution model where you don't depend much on your, convective parameterization and erroneous closure, okay, then you can do a better justice to this type of mesoscale convective system in cloud. Actually, this is the observation, and this is the IFS. Okay, this is a snapshot of 2008. So model, it's not that model doesn't do. Model definitely can do, but we have to adopt the right strategy. This is from my friend Hiroaki Miura from Jamstack. Okay, here also actually they have a very high resolution, 7-kilometer kneecap. Later on they ran it in 3.5, not operational but experimental, and you can see you can very easily identify that yes, you see the model. I mean, whatever, I don't know which one is model, which one is observation. If I ask, very difficult, but this is observation and this is model. Okay, and you can say, aha, this is here. It is doing very good job. It is capturing the the ITCC well, even it is capturing the clusters well, and so on, because we have gone to really very good and we are trying to resolve the convex. Okay, so anyway, I skip this. So basically, it is the problem is between resolved physics and the parameterized physics. Actually, if you read Jules Charney's paper 1949, he mentioned the small scale noise disturbances of the atmosphere create difficulties for the numerical integration of the equation of motion. For example, there existent demands that very small time differences. I mean, that time he is adjusting. Now, this is another paper by Nature. Here also you can figure out that he basically emphasized that if you increase the model resolution, what all are happening? The model complexity increases, and if we go towards larger scale, okay, so the issue is how do I connect turbulence to interannual variability of oxygen? Okay, you see there is a whole lot of things. Computing comes into picture, coupling comes into picture, parameterization comes into picture for some scale, not for some other scale. So one message is coming out from here is that you cannot have one single prescription for everything, right? So it has to be scale dependent. It has to be scale aware. Okay, that's what we are now using, okay, in 6 kilometers. So anyway, so now the question is, why do some models capture the organization better than others do not? Again, from observations and model, you see here is a cloud picture from a flight, and you can see these are the clouds falling within the grid, of which the grid doesn't have any idea. But there are certain clouds organized for a cloud, okay, which grows across the grid that you can resolve. Okay. Now, this is a picture. This is actually from Brian, Dr. Brian Mapes. He borrowed from his website. He's beautiful. And this picture I took somewhere when I was going in flight. You can actually see there are multi-layer clouds, right? So see here there is a cloud, there is something here, and there's another layer, there is overshooting. And look at this cloud of which Brian has taken picture, and there's the marine stratocumulus. It remains for months. So all these are part and parcel of our climate system. Okay, so this actually emphasizes on multi-scale nature of cloud. Now, if we don't do that, as I already showed, the models are not doing that. What happens is like this. This is a scatter plot of Wheeler versus rain rate. Any student can do that. You have rain rate from trim, you have Wheeler from NOAA. You plot it, okay, at different times, 10:30 AST, 11:30, 17:30. You see, observation is suggesting the cloud is becoming deeper, right? Because OLR is decreasing and the rain rate is increasing. Quite natural. When cloud becomes deeper, more precipitable water and more, rain rate. But you see the model, what it is doing continuously all the day. It is producing the same type of, okay, it's constantly raining similar. So this is actually kind of schematic cartoon. The clouds are not becoming deeper. Okay, it's kind of remaining of similar. This schematic, this animation will give you an idea. Ideally, see, it should happen like this. Okay, so this is shallow to middle, moderate, middle cloud, deep cloud, and in steady form. and then you get a complete, multi-scale structure, and you get the organization as an outcome. Now, as I told already, that convective coupling. This is an example. This is an example. So Kelvin wave is a convectively coupled wave. If you plot in ACARR data, you get a very prominent Kelvin. But you plot any of the couple models, CMIP6 or even CFS, you will struggle to figure out the Kelvin. Okay, the westward propagating Rossby waves are overestimated. Okay, and the mixed Rossby gravity wave, which actually helps, triggers the somebody was talking about synoptic scale disturbances, and you see they're completely non-existent in CFS. This is another problem, but connected to the same thing. Okay, and this is the same thing. Somebody was talking about synoptic. See, you see, this is the GCP synoptic scale variance. This is the ISO variance, and you see in the model the synoptic variance is highly underestimated, whereas ISO variance is overestimated. Okay, so another thing, another important factor is the cloud radiative interaction. Okay? We have to have a very good, very efficient cloud radiative interaction. So if you have this multi-scale cloud life cycle, convective life cycle, or multi-scale cloud, okay, then you get this cloud radiative interaction, okay, and that is connected with your radiative balance. Okay, so all are connected, okay, but the story starts from this multi-scale organization. Okay? So Arakawa actually realized by 2030, okay, that his closures are not working. His convective quasi-equilibrium is not working. And he suggested that, see, you guys go from GCM to GCR, okay, and use a unified parameterization. What does it mean, unified parameterization? It will work for 1 kilometer also, and some form of it will work for 100 kilometers. Use a unified parameterizations are also vertical, okay, right from boundary layer to deep, and GCRM. So that's GCRM example I already showed. The other thing is the MMF, mean multi-scale modeling framework, is nothing but super parameterization, which we also tried for CFS. And we actually, I cannot go into the detail. You can I have given the reference, already shared the PPT with Dr. Vilas. Please have a look. Give 30 minutes, 40 minutes, 1 hour time. Collect all these okay references. Okay, if you have any problem, you email me. So anyway, so this is the concept of super parameterization, and we applied for India. And if there's a lot of engineering, I am skipping all this. Now, if you do that, okay, we could actually improve the synoptic, drastically improve. Okay, we also improve the ISO variance. Okay, and why it is happening? This work I could not publish, but I did it like that. I did it when I was visiting in 2019 JPL. Actually, I analyzed the tendency of the CRMs, okay, and I found that the first mode of the CRM is a shallow mode. Okay, the second mode I have not shown here is the congestion, and third mode is the deep. So it has a very clear the CRM tendency very clearly resolved the three-mode structure of the cloud. And if I reconstruct them, okay, in the and take the composite, okay, you see, I see very clearly there is a northward propagation, and ahead of it is, as I have said, the this the PC1 QC, I mean ice, okay, ice and water, okay, so they are like lagging and leading. Okay, so this is purely because the CRMs are resolving the cloud, so it is capturing this northward propagation better. It is capturing the cloud structure better, and then finally it is improving the synoptic variance. Okay. Okay. Time is very short. There is a role of cumulus congestion. Okay. I cannot go into that, but what we have seen from VIRS, please read this paper. Okay. Walleta, the trim VIRS congestion data. You will see that so over Amazon and everywhere, the congestion, and also over India, you can see the congestion is central India, peaking around between noon, okay, 12 to 14 hour IST, okay. And if I don't have these congestions, okay, I cannot have the diurnal peak correctly. That's what happened in most of the model. We don't get the diurnal peak correct because we don't have this missing link. Okay. And this is another paper by Jiang et al. 2015, where he has shown the, this is from International Space Station, data from his SMILE, millimeter limb emission sounder on the International Space Station. Please read this paper, okay? Jiang et al. 2015. You will see that they have written, you see, these organizations, okay, but they are not in, correct phase because the models are not cloud ice correctly, which is observed in ISS, okay? Okay, so this is the nutshell, okay? The real world looks like this, but model looks like this. There are many gaps, okay? And you see, even the cloud interactions is affected, everything is affected, okay? This is from my friend Frankly from JPL. The same thing, okay? So somewhat similar to what which one paper you and from you get from microwave limb sounder, MLS, and many other AIRS and so on. This would be the structure, okay? This would be the structure. Okay, so now let me go fast. If I do so, okay, now organize in the last few minutes. We all know that extremes are increasing. You people know better than any one of us in India what is happening in Kerala. And these are papers very well known: Goswami et al., Rajivan et al., and Roxy et al. 2006, 2017. So all are suggesting unanimously there is increasing. And this is from our paper in weather forecasting. We showed that the model, irrespective of Europe, UK, US, nobody is doing good job. Nobody is doing good job. Okay? And we were very surprised, that what was happening, that we saw. Now also, if you go and check the precipitable water, okay, column integrated precipitable water on 2018, 2019, August, when heavy rain was happening, you will see it was very less. It was close to zero. Question is why? When so much of rain is happening, why precipitable water is very low? This was actually perplexing us. Okay, later on we understood that it is nothing but moisture. Go back to Yanai et al. 1973. Okay, so basically what was happening is that this is very low QDP. Okay, so basically what was happening is del dot Q VDP was completely getting converted into precipitation. Okay, and no model is able to do that. So this conversion. Now here you see from the paper. Okay, this is observation. Okay, there was a role of propagating cross behavior as well. Okay, and you see this is observation 2018, 2019. This is rainfall. So look at this precipitable water. Okay, close to zero. Both 2018 and 19. And you see all these models, they are doing all sorts of useless things. This precipitable water is zero, but it's not able to generate that amount of precipitation from the moisture content. That's the problem. So it is again goes back to organization. There is also a role of stochastic concept. I don't have time to get into that. Please look into this. There are papers which deals about the stochastic nature, and we also have done that, okay, in CFS and many things. And we found that if we do this stochastic, then models really improve. You see here, this Kelvin wave, you see the mixed cross decapitive wave, which was not there in CFS. The organization improves. And somebody was talking about the low cloud in southern hemisphere. Look at the bias. Okay, when we use the stochastic and add a low cloud, okay, the bias globally improves significantly. Okay, we were really surprised and very pleased to see that. Okay, and now, so there was a paper, very recent, okay, observed link between atmospheric cloud radiative effect and mesoscale organization. Again, I don't have time to explain this. I will request all the students to please go through that, read many papers. Okay, and this is possibly last 1 or 2 slides. Intensification of daily precipitation extreme from more organized convection. Very recent paper by Beyond Steven, my friend, and many others. Okay, and what they have actually shown, you see, they have actually used IMERGE data and ICON model. There's a German model. This is atmosphere only model, and this is atmosphere ocean coupling. Okay, and they have derived several index, okay, IORG, okay, or AORG, various index. It's not going to be still, it is And those index actually represents the amount of organization. See, if you ask me, how do I measure convective organization? It cannot be explained, right? So an index is defined. Okay, and many people are using it. Okay? Now, what is interesting here? You see that both this icon is a cloud resolving model. Okay, and you see it is very accurate, irrespective of whether it is atmosphere only model or coupled model. It captures organization very accurately for 95th percentile of the. So they have demonstrated that for a very high quantile rainfall distribution, this the convective organizations resolve better in this icon model in cloud. So this is our number introduction. They were saying that the global 6 kilometer model. So we were just trying to see this is one 22nd August. You see this. This is the Bharat forecast system. So you can see the rainfall persistent day 5. As in GFS, the rainfall doesn't show up by day 5. Okay, and so yeah, so I will conclude by saying that the scale gap in resolving organized convection in the climate arises due to lack of parameterizing or resolving. This is a problem till today. The cloud additive interaction, the diurnal through synoptic to large scale interaction and feedback is very poor, even in current latest model, which seems to be improving with global cloud resolving model approach. Okay, if we try to resolve it. So, for better accuracy extremes, the following are essential. One, the multi-scale cloud and convection approach. And stochastic, it has to be there. We cannot be kept closer, or it cannot be relative. And resolving the cloud additive feedback from diurnal to synoptic scale is very important. Okay? And lastly, I thought I will explain a little bit, but I don't have time. Is AIML based hybrid approach, okay, also appears to be doing very good job in resolving this multi-step process. Please read this Stephen Rash et al. Paper of 2018. I think, yeah, so I think that's the last. Stop here. I'm sorry if I have taken you. You can ask any question. Yeah, thank you.
Thank you for the informative presentation, sir. Any questions from the audience? Since we don't have any more questions, so we'll move on to the next panelist, that is Mr. Nandulal K. He is a project fellow pursuing PhD in atmospheric science from Sri Krishna College, Guruvayur. His research focuses on lightning and convective activity over Kerala with a particular emphasis on influence of dynamics and thermodynamic drivers. He investigates variability of lightning, aiming to identify key precursors and influencing factors. He will talk about the spatial and temporal characteristics of lightning activity over Kerala and its dynamical and thermodynamical attributes.
Good evening. I'm going to present the spatial and the temporal characteristics of lightning activity over Kerala, which is one of the active lightning hotspot in India. And also its dynamical and thermodynamical attributes that leads to the that can support the or that can explain the lightning activity also explained here. So So basically, the lightning is transient electrical discharge from the charged cloud in the atmosphere, which is the cumulonimbus cloud. So in this section, I will give a basic outline that through the section, I am explaining the spatial and temporal variation in lightning activity over the Kerala region, and also the thermodynamic variables like K, that is indicator of convection, and K index, and then dynamic variable vertical velocity or omega. Such are explained in the following section. So as we know, this particular figure shows the lightning activity over India, which is collected from the TRMM list data for the period of 1998 to 2013. It shows that the lightning activity over Kerala region is particularly high as compared to other regions, which is about more than 66 lightning flashes per kilometer square per year. And this is the annual cycle of lightning activity of India for 1998 to 2013. So, which shows the highest lightning activity over the India region is observed in the May, which is the primary peak, and secondary is observed in the September. So, why should I include this figure? Just to show whether the characteristics of lightning activity over India is same as that of Kerala or not. So that is why I include this figure. So uh, this is the spatial distribution of lightning activity over Indian region as based on the earlier annual cycle. That is the highest lightning active peak month, that is May, and is 1 month before and 1 month after. Then the secondary peak is observed September, and 1 month before and 1 month after. That is shown in this figure. So from it is clear that in Kerala region, the active lightning month is not same as that of the Indian region, which is in the April month shows the highest lightning activity in the pre-monsoon season. And the secondary is observed in the October. But considering the India, which is different, which means that based on its geographical features, the lightning activity is different over different locations. That is why it is explained it. So this is the temporal variation of lightning activity over India for the period. So which shows that the lightning activity is increasing, shows an increasing trend, but which is minimal, not as a considerably increasing, but it is a minimal increase shown the over Indian region. So the second one shows the April, May, June, and third shows the August, September, October. These also which shows that it is increasing. It's for the primary peak, that is April, May, June, it is trend is significant for that 99% confidence level, but for August, September, October, which is not that constant, not much increase in trend, which is in that confident level. So next is move on to the Kerala region. So that is the active lightning hotspot that we observed from the India map, the first shown figure. So this figure shows the lightning activity for the period 1988 to 2013. And the next one is the elevation. So very basically, it was reported that the characteristics of geographical features of Kerala, like the proximity of Western Ghats mountain and the moisture transport from Arabia Sea to the Western Ghats is conducive for the formation of CB cloud. CB cloud, the very that is already explained in the morning session by Ravi sir, and Uma ma'am also explained. These are thundercloud is the main characteristics for the lightning activity, which is result of the lightning activity. So here, the CB cloud for the formation of CB cloud, this geographic feature is main important. So in the first figure, it is clear that the highest lightning activity is observed in the Kottayam Idukki region, and minimum is observed in the Thrissur Palakkad region. So what I just point out that it's Western Ghats mountain stretch is supporting, because here this particular region is the Palakkad here. So here the elevation of the region is less than 150 meter only. So for this particular region, the formation of CB cloud is very less. So that is why that result lightning activity is found relatively very less over this particular region, that is Palakkad and the Thrissur region, which is less than 10 flashes per kilometers per square per year only. But for the Kottayam and Idukki region, it shows more than 60 lightning flashes per kilometer square per year. For here, the terrain, it is clear that is the highest elevated region, and the slope is also very favorable for the CB cloud formation. So next, on to the dynamic cycle. So it shows that the highest lightning activity over the Kerala region is happening in the afternoon hours from 3 p.m. This is because one more thing it point out that the formation of CB cloud is happening in the late morning hours to the afternoon hours, and that resulted lightning activity in the afternoon from 3 p.m. So this is basic idea that can fetch from this particular figure dynamic cycle. And the next one is the annual cycle of lightning activity with its special variation is shown in the IRAHA. So here, the highest is observed in the April month, and the secondary peak is observed in the October. This is for the period 1998 to 2030. So based on this annual cycle, the next figure is given here. So it shows that the lightning activity over the highest hotspot we have next, just before explained, that is Kottayam and surrounding region, begins by 0.09 lightning flashes per kilometer square per day, and which is increases thereafter and reaches maximum of more than 0.3 lightning flashes per kilometer square per day by April, and thereafter it is decreasing. So this March, April, May, that is the pre-monsoon season, is the highest lightning observed season in Kerala. This is just because the this particular season, the local heating is very much supporting for the CB cloud formation and the resulting lightning activity. November to the September, October, November, lightning activity is relatively less. This is because this local governing factor is not that much supportive for the CB cloud formation as compared to pre-monsoon season. That is why the lightning activity over this season is relatively less. Even though in October, it is reported around 0.06 lightning flashes per kilometer square per day, or in Kottayam and surrounding region, as well as in the Malappuram, Kottayam region also. Next, it is going to explain is thermodynamical variable. Like for the lightning to happen, the convection is important. So very much related variable is K. So this is the spatial distribution of convective available potential energy. From it is clear that the Kp over the coastal side of Kerala region is more than 1,400 joule per kilogram. This which or in April. So it supports the convection to happen, and that result in the CB cloud formation and the resulting lightning activity. And by the end of pre-monsoon season, which is decreasing, so its intensity is also be decreased. Lightning intensity also be decreased, and which agreement with the earlier figure as observed. And for the September, October, November, the value of the Kp is relatively less, which is about to 550 to 650 only in the coastal side of Kerala, especially in the October. But still we get lightning activity, and which is even is comparably minimum as compared to pre-monsoon season, we will get lightning activity, and Kp itself is less. But what the other factor governing for the lightning activity or the CB cloud formation, even the less convection happen in this particular month, because it other factor like uh, vertical velocity or dynamic factors is highly influencing in the post-monsoon season. That will be explained in the next section, next figure. So this is the spatial distribution of K index. So it shows that the throughout the month, pre-monsoon as well as in the post-monsoon period, the K index value is above 30 Kelvin. So which shows the strong instability that prevailing over the Kerala region that support for the lightning activity. So next is the dynamical variable like vertical velocity or omega. Its negative value indicates the updraft and positive value indicates the downdraft. So here, these are the active lightning region observed in the figure. So during the active lightning month April, the strong updraft is observed in the lightning active zone. So from it is clear that the dynamical factors is highly influencing for the formation of CB cloud, and that may result the lightning activity. And similar as observed in October, as compared to April, the October vertical velocity shows strong negative value. This means that as compared to pre-monsoon, apart from the case, the dynamic factor, thermodynamic factor, apart from thermodynamic variable, the dynamic factor is highly influencing for the formation of CB cloud. And this is the spatial correlation of lightning activity with CAPE and K index. And this particular figure is done by using the LISOTD dataset for lightning, and that from ERA5 reanalysis data, CAPE and the K index. So here itself, it is clear that the correlation of CAPE and the lightning activity is strong in the month of April, and that also in the October. So one more thing, it is reduced from that. Its correlation, the asterisk symbol shows its correlation value is significant number of 95% confidence level. So its higher confidence level observed in this causal side indicates that the convection and the lightning activity over the Kerala is supported by wind also. So that will explain in next section also. So next is the K index, correlation of lightning activity to K index. So this also shows the highest correlation of lightning activity in active lightning month like April and October. So here I didn't include the vertical velocity correlation just because the space, which is not that much robust to show the correlation of lightning activity vertical velocity. Its spatial plot is only supportive for the more clear picture for the presence of atmospheric instability. That is why I didn't incorporate the correlation of lightning with omega or vertical velocity. So this is the spatial correlation of lightning activity with NOVA OISST, as well as its contour line shows the climatological value of NOVA OISST. So this shows that the strong correlation is observed in the April and May, and then October and November over the coastal side of Kerala, sea region of Kerala, and as well as the SST value above, climatological value of SST above 29.6 degree Celsius is supportive for the CB cloud formation by the support of wind. That is, just I mentioned above that, even the Cape is shown highest value in the coastal side, and as well as the SST above 29 degrees Celsius is observed in April also. By the aid of wind, it supports the formation of CB cloud over the Kerala region. Also, the geographical features like the Western Ghats is supporting for its formation, and that is resulting in the lightning activity. So this is the moisture transport from 1998 to 2013. It is from the 1000 to 300 hectopascal it is plotted. So the strong moisture transport from Arabian Sea side over the northern Kerala side is observed in April, and which is intensified by the end of pre-monsoon season. And on the October, the moisture transfer from Bay of Bengal is significantly supporting in the northern Kerala side, and that from the Arabian Sea supporting the southern Kerala side. And by the end of this month, I mean November, the strong moisture transfer from the Bay of Bengal side is supportive for the CB cloud formation. So next is the temporal variation of lightning activity from 1998 to 2013. This is particularly for the annual throughout period, means from January to December. So it also shows increasing trend, even as value is minimal, it shows an increasing trend and it's very significant above 98% confidence level. Next for the March, April, May, that is pre-monsoon, and other for the September, October, November. This also shows the significant increase in trend, but its value is minimal. That is, so I'm not much going into detail to this. So to the conclusion, The highest lightning activity is observed in Kottayam region and the surrounding area, which is about more than 70 lightning flashes per kilometer square per year, and less is observed in the Palakkad region and the Thrissur, so which is less than 30 kilometer flashes per kilometer square per year. And the lightning activities peak around the 3 p.m., which shows that the convection is happened the late morning to afternoon hours. So that result lightning activity by increasing lightning activity by 3 p.m. over Kerala region, and the case and Cleveland also shows strong correlation with the lightning activity. So which means that these variables are very well supportive to identify or track the lightning activity. And the omega, the dynamic variable omega or the vertical velocity at 500 hectopascal is very well supportive for the spatial pattern is very well supportive for the identifying the updraft over the particular lightning active region, and thereby identifying the CP cloud formation and resulting lightning activity. And the SST above 29.6 degrees Celsius significantly contribute for the convective activity. So this is also a significant variable to identify the lightning activity, because this above this particular value the convection is higher, and the resulting lightning activity also be higher. Then the moisture and transport analysis is also be observed, which shows that during the pre-monsoon, the moisture from Bay of Bengal is significantly supporting, and September, October from Arabian Sea with the Bay of Bengal become the prime source again in by November. So in general, the here this particular study explained the spatial how the spatial and temporal variation of lightning activity is observed in different seasons, like in pre-monsoon and post-monsoon period. That these are the active lightning period in over Kerala, and what are the dynamical and thermodynamical factors that support for this lightning activity. So basically, it is clear that the convective value potential energy and the K index is the very prime variables that give a clear idea about the lightning activity over Kerala. And then the moisture transport also give a clear picture for the transport of moisture that supportive for the CP cloud formation. And one more thing is the dynamic variable omega and the SST has significant role in identifying the CP cloud formation over this region. And this is all. Thank you.
Thank you, Nandar. That was very informative. So we can have a few questions. If anybody want to ask some questions. So, okay, I hope there's no questions. So now I invite Dr. C.A. Babu to give a token of appreciation to Nandu. Moving on to the last presentation of today. Our next panelist is Ms. Shilpamol DS, who is a Junior Research Fellow at Advanced Center for Atmospheric Radar Research, CUSAT. Her research primarily focuses on mesoscale convective systems, monsoon heavy rainfall events, and satellite-based weather observations and analysis. She is actively involved in the study of atmospheric processes that influence extreme events over the southwest coast of India. She utilizes high-resolution satellite data to track and characterize convective systems associated with Indian summer monsoon. Over to you, Shilpa.
Good afternoon, everyone. My name is Shilpa Diaz. I'm research scholar from Advanced and Report Radar Research. So today I'm going to discuss my recent research findings, which is titled as Characteristics of Mesoscale Convective System During Monsoon Extreme Rainfall Events, Case Studies from the Southwest Coast of India. So before I jump into my research findings, I would like to give a brief introduction about the mesoscale convective system. Okay, you guys already show that this figure in multiple presentation, and also they have well explained during their presentation. So I won't explain that much. I so herein stated that mesoscale convective systems are organized convective storm complexes extending over several hundred kilometers and producing large areas of convective and stratiform precipitation. The precipitation and the structures of mesoscale convective systems are basically depends upon the region of genesis and the underlying process. They are typically driven by the deep moist convection and the vertical wind shear. Why these mesoscale convective systems are responsible? Because they are responsible for the large proportion of tropical through mid-latitude extreme precipitation events. Thus, they plays an important role in the hydrological cycle. So here I have listed some of the structures that can of the mesoscale convective system. So it is clear from the structure. The first one is mesoscale convective complexes. It is a cross section, and beside is the corresponding radar or satellite imagery. And the second one is the square lines. As we all know that they are the narrow band of deep convection, especially in the thunderstorm clouds, and the other is bow echo and training line and the back building. So they usually consist of high cloud forms, mostly in cumulonimbus clouds, but also they have seen in cirrus and orthostratus cloud, which is also explained in the Rajivan Sar. So their size is from 20 to 40 kilometers to several hundreds of thousand kilometers, and their cloud top height reaches 13 to 40 kilometers, sometimes up to 16 kilometers. Mesoscale convective system, they are also temporally variable, specifically in their diurnal cycle overlap. They are typically initiate in the afternoon or early evening, and they are reach maximum intensity overnight and dissipate within the few hours after sunrise. So today I'm going to discuss my recent work, which is public natural hazards. So these are the data have used the brightness temperature sat imagery from and which is available in 3 kilometer spatial resolution and 50-minute temporal resolution. And immersive precipitation product, Saras OLR dataset and daily IMD grid rainfall dataset. And finally, the ERA5 reanalysis wind data. So coming to our methodology, we have more concentrated on southwest coast of India. We have tracked the MCs from high temporal and spatial resolution MSG to Siberi satellite. We have used the brightness temperature channel IR 10.8 micrometer because brightness temperature are considered as the proxy for the detection of MCS. We have used the commonly used detection criteria, that is where the brightness temperature falls below 230 Kelvin and the spatial coverage is exceeding from 10 to the power of 4 kilometers square. So these figure clearly explain the different steps that involved in the tracking of mesoscale from satellite imagery. The first figure is the actual imagery from the satellite. The color bar is the brightness temperature. And the first step is the feature masking. In that step, we have applied a mask which is detect or mask the region where the brightness temperature falls below 230 Kelvin. After that mask, we have applied to the actual imagery, and it will segment the region where where the features are extracted from that actual imagery. So after that, we have calculated their corresponding areas. So we have also analyzed to check the background condition. We have find the vertical integrated moisture flux using this formula. So this figure indicate the time series of area average daily rainfall over Kerala for the monsoon seasons of 2018 to 2024. So from during the period 2018 to 2024, we have calculated seasonal mean and the prominent rainfall fix, which is above 1 sigma standard deviation, was considered as the heavy rainfall fix. From this figure, we identified the 7 heavy rainfall events. Out of these 7 heavy rainfall events, we have here I am explaining the major 3 extreme rainfall events which is occurring 2018, 2019 and 2024. As we all know that 2024 we had a heavy rainfall over the Wayanad that will lead to a devastating landslide. So here I am also explaining that MCS characteristic over that region. So coming to the result and discussion, these figures shows the event occurred in 16th August 2018. The figures A represents the daily average brightness temperature and the B is the distribution of MCS. The position denote the center of MCS and the size and the color bar of the circle denote corresponding area and the C is the accumulated rainfall. So from this figure, we can see that in a we have as observed from the average brightness temperature, there is a north oriented cluster extending from central Arabian Sea to central Kerala. Within average area covered by the MCS, it is in order of 10 to the power 10 meters square. So due to this presence of such a robust MCS near the coastal regions, there will be a heavy precipitation over the central Kerala region, which is noted in the range of 200 to 250 millimeter per day. Also, we can see the another band over the oceanic region, but being far from the inland region, their contribution to the land precipitation is minimum. So, as it is clear from the figure, the impact of organization of mesoscale convective system associated with extreme rainfall events on 16th August 2018, we can clearly see that a north and an extreme prominent rainfall patches extending from coastal region to central Kerala region. So coming to the 2019, we identified the 2 heavy rainfall events. First is the 20th July 2019 and the second one is the 9th August 2019. So in the first figure, we can see that on an average, the entire Kerala coast and the inland regions are covered with the average temperature of 260 Kelvin. So that we only get the MCS which is predominantly situated over the Arabian Sea. So in that region, it will noted with a heavy rainfall range over a confined region. But if you look close into the north coastal regions of Kerala, we could find a small cluster of MCS which having area expansion in the order of 10 to the power 9 to 10 to the power 10 meters meter square. So that will attribute the heavy rainfall over the Kerala coastal region, which is in the range of 100 to 200 millimeter per day. But coming to the second case, which is very unique as compared to 2018 and the previous 2019 event. So it is very clear from the figure that there is a massive aggregation of mesoscale convective system covering in the large area is prevalent over oceanic and the coastal regions. So if it is compared to 2018, there has been increase in the frequency of MCS with an area average exceeding 10 to the power 10 meters square. So that will constitute the heavy rainfall over the north to central regions of Kerala. So this rainfall received over northern Kerala is approximately 5 times the magnitude observed during the 2018 episode. So most importantly, as I said earlier, we have also investigated the extreme rainfall associated with a massive landslide that occurred in the early morning of 13th July 2024 in Wayanad. These figures are correspond to that incident. So from the clear, our primary object was to determine whether the MCS clustering observed during 2018 and 19 extreme rainfall events on the southwest coast had reoccurred in this case. So as we have clearly explained that from the figure A, average brightness temperature, it is clear from both land and the coastal regions are covered with a massive brightness temperature which is low below the 230 Kelvin. And if we look corresponding figures, that is B, the size of the MC is clearly stated that 2000 similar to 2019 extreme rainfall events, the MCS aggregation and it will increase to the land region with a average area coverage of 10 to the power 10 to 10 to the power 11 meters square. square is visible over the northern Kerala coast on early morning of 13th July 2024. So that will lead to heavy rainfall over the northern region, especially in the Wayanad region. That will lead to a catastrophic landslide over the region within a span of 3 to 4 hours. So, only the occurrence of MCS does not lead to the heavy to extreme rainfall events unless it persisted for an extended duration. So, analyzing the diurnal cycle will shed some light into that point. So, these three figures shows the diurnal cycle of the extreme rainfall events that occurred in 2018, 19, and 2024. As it is clear from the figure, in 2018, the MCS are situated almost in the size about 10 to the power 10 meters square. So the corresponding rainfall is having high and low values. But if it is into the 2019 case, we can see that the MCSR stays above the 10 to the power 10 meters square, and also that will lead to the heavy precipitation over the southwest coast of Kerala region. But if we more look into the for the event 2024 event, MCS activity was predominantly after the 16 local time, that is, which is 4 p.m. and it is persisted until the early morning of July 13, 2024. So, in this figure, we can see that the precipitation amount scales varies with the strength of MCS, and it gives the transition from heavy to extreme rainfall events, which is facilitated by the persistence of this MCS for the several hours. So, in order, it is essential to check the weather conditions of these extreme rainfall events, which lead to the heavy rainfall over the land region. So, we have calculated the vertical integrated moisture flex. So, we have find that these three extreme rainfall events, we found a massive and a strong moisture convergence near the coast. Sorry for the inconvenience. So, I'm here talking about the moisture conversion. So, we found that in these extreme rainfall events, we have identified the and intensified moisture convergence observed near and inland regions of south coast of Arabian Sea near the land region. So, we have also analyze the vertical velocity. So we found that a very strong updraft from surface to the mid-troposphere is evident along the 9 to 12 degree north in 2018. So the ascending motion within the lower to mid-troposphere is very weak for the other event. So I'm concluding our research that these are the major points for our recent research work, that is analyzing of impact of heavy rainfall events, particularly over Kerala, reveals that the monsoon seasons of 2018, 19, and 24 marked by floods and other natural hazards. These associated with the extreme rainfall during these events were extensive and well organized, covering an area ranging from 10 to the power 10 to 10 to the power 11 meters square, primarily over the south coast of India. The study underscored that the MCS aggregation over coastal and the inland regions of Kerala exceeding 10 to the power 10 meters square are likely to bring the torrential rain, thereby facilitating disaster management and mitigation method. This study holds relevance in the context of evident climate change along the southwest coast, and the continuous monitoring of MCS evolution through satellite observation enables the identification where the region is susceptible to heavy rainfall, adding in nowcast. Before I concluding my presentation, I would like to show a GIF presentation. It is. So this is the evolution of MCS that is occurred in heavy rainfall events associated with the torrential landslide over Wayanad on 13th July 2024. Here we can see that the MCS are persisted in the atmosphere for a long period of time that will lead to the heavy rainfall over that region. I think this is clear. Thank you.
Thank you, Shilpa, for the interesting presentation. Are there any questions from the audience? Okay, I would like to invite Professor Babu sir for the handing over a memento to Shilpa. With this, we have come to the end of the panel discussions for the day. As we bring this enriching day to a close, it is time to pause and reflect on the insights, ideas, and questions that have emerged across our sessions. To offer closing reflections and guide us towards the path ahead, I now invite Dr. Tara Prabhakar, the Chairman of the International Commission on Tropical Meteorology, for the concluding remarks.
Sir, are you here?
Yeah, I'm here.
Yeah. Actually, we are waiting to conclude the sessions.
Okay.
If there is no more discussions, I think we can wind up the session.
Okay.
So, is there
Okay.
any questions or
No, I have no question
Yeah.
actually, but I would. I have just one suggestion. See, the students, the last two talk, this the last two students, they were very good. Their topic, etc., are excellent. Okay, but but the student who was explaining the lightning with cape and index, K index. Okay, so tell him and this thing to do a very good detailed literature review. Okay, because the cape, cape is such an index which can give you a lot of false alarm, because in the tropics during boreal summer, almost all the days of monsoon, cape is high, but that does not guarantee heavy rain or thunderstorm or lightning. Okay, so there are much more than cape. That's one. K index is a very old index. Sometimes it works, sometimes it doesn't work. Okay, so tell them to utilize. I will I will forward you on paper. So like you have this wind profiler where you have the vertical velocity, which that the last speaker was showing. Okay, and we showed in our weather forecasting paper. They should take help of this vertical velocity in their index. Okay, they can define a new index. There is no harm in it, because you have now at least, I think, 10 years or maybe 7 years or 8 years of data. From there, along with thermodynamics and vertical velocity, they can define a new index for Kerala thunderstorm. Need not depend on Cape and K index. Okay, that is one suggestion. Suggestion two to the last speaker. She is doing excellent. Okay, very good presentation, excellent topic. But this, see, I mean, see, sometimes what we do, I mean, I also did many times, when I look into thunderstorm over West Bengal, thunderstorm over Delhi, thunderstorm over Pune, we don't see the large scale. So we should keep a vision in background that how to connect it with the large scale. Okay. Yeah, that's what she is trying. She actually tried that for 18, 19, and 2024. Okay. And also these the moisture convergence that she showed, that was also very good. But that actually comes from that ENI equation that I showed. So these are some small suggestions. I think they are very promising budding scientists. Future is in their hand. So they should actually put more emphasis and give more insight, so that these limitation and deadlocks can be overcome. But it is very nice. I enjoyed. Excellent.
Thank you for this encouraging words. So I think we can wind up the session. So let us.
Okay, thank you. Okay.
All the experts who have delivered their lectures today. Actually, we have started with a philosophical approach in this multi-scale interaction of convective patterns and organization by Professor Bang. So he started from a philosophical view of convective organization. He is taking to that evolutionary theory and some kind of ecosystem approach, ecology of convection. We started from that, and we have discussed the microphysical aspects with the multi sunlight relations, followed by Dr. Rajiv had a few presentations on the multi-scale organization of convection using radar, and then representation in the model, the microphysical representations, how they are impacting the propagation of tropical cyclones, and then followed by that, I have given these 2 slots for the students because they both published good work recently regarding natural, both in natural reserves, lightning and the mesoscale convection. And present they were before this. And finally, in the last session, the organization and the structure of convection in our model and approaches like superparameterization, and now we are moving to kilometer scale model with ADS and all. So these are still, I would say that the area of convection is still not understandable to all, because we all talk about a different type of interaction and multi-scale interaction, but still it is a fascinating subject with a lot of opportunities, a lot of challenges. At the same time, it offers you a lot of opportunities. That is why all students are here. You have to take up these challenges. I think all enjoyed this session, and I'm thanking ICTM for giving this opportunity to conduct this seminar organized by Cochin University of Science and Technology. And I once again thank all the experts and students and other research scholars who have joined offline and online. Thank you very much.
Thank you, Vilas. Thank you.